Hi everyone, welcome to this SAS Global Forum 2020 online presentation. In this presentation, I'll be talking about an overview of container technology with a quick introduction to a lot of different things about containers out there. My name is Brent Laster. I'm an R&D director in the R&D DevOps organization at SAS, and I manage multiple teams working with deployment, DevOps, and other focuses like security out there. As well, I do some global training in open source and DevOps technologies and practices, and this presentation is based on some of my previous trainings out there. I hope you find it useful. In this presentation, I'll be talking about a lot of different open source and container related technologies out there. We'll start off talking about the basics of containers. What is a container? What makes them up? What is a container image? How does that differ from a container? How do we create these things and how do we think about them? We'll talk about those in the context of Docker as well, with Docker being the application that wraps the formality or the way to interface with and create containers into an application itself out there and simplifies using some of the underlying Linux container technology to enable us to work with containers easily out there. We'll then move into talking about Kubernetes. What Kubernetes is, as I say in the presentation, we can think of it almost like a data center for containers out there in terms of managing the individual containers and running in things we call pods and being responsible for scaling, for making sure that they have new ones spun up if there's a problem with it, that we scale up or down, and the kinds of things that we might think about a data center managing for computers. We'll talk about the different kinds of configuration and inputs we do for Kubernetes, the ways that we can tell it what we need out there, the kinds of different objects that we use with it, the things that it supplies for us in terms of functionality. And we'll also get into how within definitions within Kubernetes, we can do things like having health checks and talking about the health of the containers running in the system and managing the resources out there available on the systems running Kubernetes. We'll move into talking about Helm then. Helm is an orchestration engine for Kubernetes, allowing us to help manage how do we reuse specifications out there. How do we have them as templates rather than hard-coded things that we can reuse and that we can supply appropriate customized values in there for us as well. Then we'll talk about another tool actually named Kustomize with a K out there, which is an alternative to Helm. It's a newer tool, but it's actually gaining quite a bit of popularity in terms of being able to help with orchestration of Kubernetes as well. It takes a different approach from Helm. Instead of parameterizing things and creating templates, it's more about adding additional layers on top of basic specifications out there and using those to build up from the original Kubernetes templates out there and add additional functionality without having to modify the basic templates that are running at the base of it. We'll move into talking about Istio. Istio is a tool for helping us achieve and implement what we call service meshes, talking about microservice meshes. How do we use Istio to be able to control communication, networking, encryption, those kinds of things out there across a wide series of microservices running in Kubernetes out there, and what is the value that it brings to us. We'll help you understand the different parts of it with a lot of different visualizations and such as well. Then we'll move into talking about Kubernetes operators. Operators are a way for us to have custom processing for custom objects or custom resources, as we call them, out in Kubernetes, things that might not normally respond in the way that Kubernetes would expect out there in terms of things like scaling or being restarted, those kinds of things. We'll discuss how operators actually help that and help manage that for us. Then we'll talk about GitOps briefly. GitOps is the idea of being able to take our specifications for things like Kubernetes and manage them through a Git process out there to give us things like the review of changes out there, being able to roll back easier within Git, being able to track who make changes and such, as opposed to a human actually working with a command line to drive changes into Kubernetes out there. And finally, we'll talk about a few tools that are applicable for monitoring within Kubernetes out there. We'll talk about Grafana and Prometheus and the Kubernetes dashboard out there. Graphical interfaces that can give us some real insight across the board into how our clusters are doing, what our containers are doing out there, and that sort of thing. So we have a lot to cover. I hope you find it useful and interesting, and we'll get started next with talking about containers in Docker. Let's start out our presentation today by talking about containers in Docker. So what are containers? Container is a standard unit of software that functions like a fully provisioned machine, installed with all the software needed to run an application. I sometimes tell people to think about containers as almost a computer within a computer. That is, in the same way you might have a laptop or a desktop that has all of the software installed on it and provisioned to ready to run applications, you can have a container as a self-contained unit ready to run an application as well, just virtually within the context of something like Docker. It's a way of packaging software so that application dependencies have a self-contained environment to run in, or insulated from the host OS and other applications, and easily ported to other environments. Because we have this container wrapping all of these pieces in there and managing the environment for us, then we can easily port that from one system to another that's able to run containers out there. Namely, any system that has something like Docker on it is available to execute them. Anytime you talk about containers, you're likely to see this obligatory picture of a cargo ship out there. The cargo ship has a set of containers on it to remind us that the containers are these self-contained units. They can be of varying types or sizes out there, and they all contain what's needed in it to run a particular application or a set of applications out there. So what might be in a container? If we think of the container like a cargo container, if we were to look inside, we might see that it has the application, the runtime, the dependencies, the settings, the system libraries, the system tools, and other pieces in there. Everything that we need to run for it to act like its own environment, act like a standalone computer there. So we have the container there, and you'll see on the side here, this is the standard logo for Docker out there. Now, a container is not a VM, meaning a virtual image out there. We'll talk in a few moments about what the difference is here, but a container works by leveraging several features of the Linux operating system to carve out a self-contained space to run in, as opposed to a virtual machine, which works through a program called a hypervisor sitting on top of the operating system and working through that to run the applications inside of it. The benefits of containers: easy to create and deploy once you define an image. Containers are based off of an image. An image is simply a provisioned set of software configured in a certain way so as to be able to support the running of applications. And once we have that image out there, we can create those containers, and they're very easy to spin up or destroy. The image serves as our blueprint for that. The best practices in continuous development, integration, deployment allow for frequent, reliable builds and deployments, meaning that when we have containers out there, we can use them in our continuous deployment integration pieces out there because we can easily spin these up, scale these up, get rid of them, those sorts of things. It helps to facilitate these notions we have around continuous development, integration, and deployment out there. They're quick and easy rollbacks due to image mutability. What we mean by that is that the image, the set of provision software that a container is based on, is considered immutable. That means that it is not changeable in there. We'll talk more about that in a few minutes, but because the image itself that we're basing the container on is not changeable, it's immutable, it's easy to create a new container based off of that if something goes wrong in the one we have. They're created at build or release time instead of at deployment time, so applications are decoupled from the infrastructure. So basically, when we have the container set up, we have the entire system running. Think of it as if you have a laptop out there, for example, with all the software provisioned on it, and when you start it up, that's like starting up a container. The image of software is always there on your laptop, even if it is turned off, but it's always there ready to go as soon as you turn it on. So when these are created at build release time and they're turned on in effect out there, then we don't have to worry about the application, the infrastructure being there or how we set that up. The infrastructure is already there by virtue of how we defined it within the image. That's the basis for the container. The containers provide observability through application health and signals, not just from the operating system. So especially when we start getting into the world of Kubernetes and stuff, we'll talk more about these sort of health signals, application health checks in there. and making sure things are running out there good. A container, because of the way it's packaged up and because of things it can monitor, it can better detect the application's health overall and give us signals about that and logs and such. Because the environment is self-contained, it runs the same on all infrastructure. You can run a container again anywhere that you have an infrastructure like Docker out there. Could be a laptop, a desktop, one of the public clouds, portable across any OS or cloud that supports containers, and you can manage the application instead of the infrastructure. Once you have your image defined out there that is supporting your application, you have the software provisioned out there, then you can focus on developing or tuning the application there rather than the infrastructure that supports it. It allows applications such as microservices to be loosely coupled, distributed, managed, and deployed dynamically. We can create different containers for different purposes out there. We can create a container, for example, for each microservice, and because of the way they interact with each other, because of the way the containers can be the self-contained environment for each one, it allows us to be more loosely coupled there and to get away from having the monolithic software stacks. Has resource isolation and effective utilization of resources out there within the container. And we have the containers that are created from images out there. They are running instances of images. So let's talk a little bit more about what a container image is. We referenced that a container image is sort of like having a provisioned set of software out there to base a running system on. Think of a container image as being like a read-only template that's used to create a container. It's like a snapshot of a container out there. That is, the image is like a pre-configured setup for the container. And then when we activate the container, when we start up a container, it's like turning our laptop on. The image is always out there and represents a snapshot, a way that things are configured and set up at that point in time. When we turn it on, then we're in a place where we can actually use it, modify things, and so on. Container images are stored in a registry, like a repository for images out there, such as a Docker registry. Images are generally considered to be immutable. That is, once they're created, the image should not be changed. If a change is needed, a new image should be created. We'll talk more about that in just a moment, but the idea here is that the layers of software and configuration and the different provisioning that is used for an image there is intended not to be modified. That is, it is specified and set up and then serves as an image that is immutable out there. When we go to actually create a container, we add in a read-write layer or a place to make changes in there. And we'll discuss more how that works in a moment. But because the images are kept immutable or changing, again, it's very easy to modify or create new containers off of those delete containers, but still have the underlying image out there that is consistent no matter how many containers we create from it. Note that immutability does not imply that containers can't be changed by configuration or environment, etc. The container that is based on the image does have this read-write layer out there that where things can be modified and changed. Container images are built up from these layers, and if you're using Docker, for example, the Docker build command is used to create images from that. So what is an image layer? We've referenced this idea of layers to build up an image here. So a Docker image is built up from a series of layers. Again, think of the images here as being the provisioning of the software that we want to have in place to run the application. We're just provisioning it for this image that forms the basis of our container, much as we might provision an image that forms the set of software that we want to stage or to put on different computers out there. So a Docker image is built up from a series of layers. Each layer results from an instruction modification in the Docker file. So a Docker file is a way in Docker to specify the set of software, the kind of configuration, the set of local things that we want to copy into our image out there. It is a recipe for how we provision this set of software that makes up the image out there. For the majority of the commands that we find in the Docker file, such as the ones that you see on the right-hand side over there, we will create an individual layer in our image that corresponds to that. If you take a look at the right-hand side there, you'll see the image file, which says starting with the from command, from Ubuntu 18.04, meaning that we're starting with that as a base operating system image. This is a particular version of the Ubuntu operating system that has been turned into a Docker image out there that serves as the base image or the starting image for us to then modify to get to the point of where we have the software provisioned the way we want it for our application. The second command is simply copying in some local stuff into this image here, running a command for us to create some other content, and then having a command out there to run this Python piece out there. So each layer essentially in a Docker file will end up creating a layer in our image out there. Layers are stacked on top of the ones before, kind of in the order that we were looking at them in the Docker file there. Each layer is consisting of only a set of differences from the last one. So if something is already present in one layer, then it's only the differences that are tied in on the next layer in there. Think of the base layer as being an OS image. If you think about provisioning a computer again, that sort of analogy, you might think of installing the basic operating system on the computer out there and then layering on other software as appropriate. Each layer in this case is going to be read-only, except for the last one, the container one, when we actually spin up a container from it. The last or top layer is that container layer, which is a thin read-write layer. So all changes made to the running container go in that layer. So if you look below the image there, you can see that we have a version of the software out there. We then have different layers for the different things that we have done to this to add up to the set of provisioned software out there. Again, the analogy might be being able to install software onto a machine to build up to the image you want. And then when you turn it on, you have the read-write layer out there. You have the user space, for example, on a machine where the user can create files and work with them. But the user is generally not working with or changing the underlying software layers on the system. Creating and tracking layers for images. So we'll look through a little video here. You'll see on the right-hand side, which is an example of actually running a Docker build command to get a set of content there and to actually create an image there from a Docker file. You can see on the right-hand side there, it is executing the commands that are noted in the Docker file on the left. On the left is the Docker file, the set of instructions for building up an image. As we go to execute them with the Docker build command out there, we have, you can see from the steps out there, it's pulling down the basic MySQL image that we're looking for. And you can see that it's pulling down layers here. In other words, that MySQL image is made up of a set of layers itself. It's our base image, but at some point in the past, someone has to find a set of layers, a set of software provisioning that went in to making up that MySQL image. And as its layers are pulled down to get the underlying base image, you can see the process happening in the stuff running on the right-hand side of the screen out there. Now, you may notice also the Docker build command has that -t option on it there. That is actually a tag option out there to give it a human-readable identifier to make it easier to work with the image. Then we see that as it's gone through this, it's actually going through and creating these intermediate containers there, these hexadecimal strings that you see on the screen. The hexadecimal strings are our IDs for the various layers that we're working with there. So you see that it actually went through step 1 of 4, pulled down the MySQL stuff. Step 2 of 4, copied over some stuff locally that we were using in there. Step 3 of 4, set up an entry point, and step 4 of 4 did a command. The idea here is that we started out with a basic MySQL image. We then copied over some scripts that whether it gets run as part of the container starting up there, it will actually create some databases for us for MySQL to work with. This is the way the MySQL image has been defined out there to understand how to do this when it starts up. Typically, when someone creates a particular image that they expect to be reused in a more general way, they will define some sort of mechanism, some sort of scripts that can be run at startup to configure or populate or do something with the underlying applications there. They could also define other scripts that run at various times there, or environment variables for information may be passed in, that sort of thing. So in step 2, we're copying over some local content that we've created and we've customized to set up the database the way we want it. Now then in step 3 here, we have an entry point which says when I start this up, what is the thing I want to run? I want to run the entry point.sh, a shell script out here, and then that will go off and actually run those pieces to go through what we copied in this case, so the way that this MySQL image is set up to work, run those, start up that script running, which will go through execute the stuff that we pulled in and copied locally to create the databases and that we want to have present in this container. Then step 4 is just a command to start with the MySQL daemon out there. But you can see that ultimately, as we're going through this, we're getting into layers for any base images that we need. We're adding on additional layers, those hexadecimal IDs, which is different steps here in this particular Docker file here. And then we end up with an actual image as a result. The actual image ID at the bottom there, you can see, and then we have a successful tagging, which means that we have applied a human-friendly name to this along with a version number out there. So how does this all tie together then? Well, if we tie it to, if we look at, for example, the basic functionality, the basic output from the steps there as corresponds to the Docker file, and sort of the history that we have using the Docker history command to see the different layers that have been used to build up this image, then we can see that when we do the step in blue here, we pull down the from MySQL, we had a corresponding action when the Docker build ran that pulled the content down from there. Then we had a corresponding layer created for that, the ID with the layer out there that consisted of that MySQL base image. As we then went through, if we look at the Docker history, we could go through and see all of the different layers that made up that part. Now you'll notice probably the missing identifier or designation there for these image layers. Missing simply means that we do not have the original layer information out there, the original layer IDs that were used to construct this. Rather, we have the ultimate ID of the underlying image once it was completed, but this was done some 3 years ago, and it was not stored, the information was not stored with it as far as the IDs for each unique layer out there. We also have then the command to copy over some local content into our system. As we copy that over out there, we can see that that step was also executed as part of the Docker build command, which resulted in yet another layer in our image out there. Then if we do the same thing for the entry point having the thing to run when we start up the container, again resulting in another layer in our image. And then finally we have them running the MySQL daemon, adding another layer in there, another action, which resulted in another layer out there. And you can also see that in the history. So ultimately what we end up with then in this sort of light green and white block here is our Docker image, which is the set of layers that resulted from running through the Docker build and provisioning software, adding in things, configuring things as we went along executing the build from the Docker file. Now, how do layers and images intersect with the operating system? So we have an image out here. Basically, layers are like, the layers in the images are like files to the operating system. The image layers, as we said, are read-only, meaning immutable. They can't be changed out there. But when we actually want to use these as the basis for a container, then what Docker would do is create a container from an image. If we run the Docker run command, we create a container from an image, and that would add another layer, a read-write one on there that gives us a place to make changes. Again, you can think of this kind of from the analogy of I have a set of installed software on my computer or my laptop. I generally am not making changes against that software. It's generally considered immutable as far as the operating system files and stuff that are installed upon it. But then I do have a user space out there, like a layer where I can actually change my content. I can store things in documents. I can download things, that sort of pieces in there. So the container layer that gets added on top of an image to create a container comes from the Docker run command. You can see here that when I do a Docker run command here, I'm running some stuff. I want to run an instance of the MySQL image. The MySQL image serves as our provision software. The container serves as a running instance of that. Again, think of it kind of like turning on a computer that already has an image installed on it and then being able to make changes and work stuff in there. Now the -e here, the MySQL root password in there, is passing in information via environment variables through the run command that the image is looking for. Again, whoever set up this MySQL image set it up so that it could actually be looking for information about, for example, the user, the passwords, and so on passed in through environment variable. That's not always, of course, the most secure way to do that. So when we get into things like Kubernetes, we'll talk about other ways to manage information like that. But this is the basic idea. So when we run this with the Docker run command, Then what happens is we get another layer added on top of our image, and that forms the container. The container has the read-write layer out there where we can work in there based on top of the read-only layers from the images. At that point, if we were to do a Docker PS, think that's looking at the processes out there, we would be able to see our container in there as designated by that ID that came from the Docker run command once we had generated the container. It gets its own hexadecimal ID out there, which is the address or the identifier for that label out there based on the image we created earlier. So the layers here, we mentioned briefly before that when we have talking about Docker and stuff in there, that we have the layers that make up the system and that they are immutable in there. And the difference that with versus from a virtual machine versus a thing like a container in there with Docker is that the container is implemented by leveraging some core functionalities of Linux out there. The Linux operating system has been around for a long time and has had containerization support in it for a long time as well. There is LXC, Linux containers out there. And what Docker does is it actually leverages its underlying functionalities, but provides a nice framework around them. The Docker file for specifying commands to use in there, the APIs and stuff for talking to them, and so forth in there. So Docker puts a nice framework around these core Linux technologies to provide the simplified container and image functionality that we've come to know, or you will come to know through Docker. So layers can be viewed as a single union of all the file systems. The first piece of the technologies out here that we rely on in Linux is called the union file system. And the union file system, since we have layers, allows us to look through these layers to find content that we need. That is almost like a path setting on a computer out there in an environment. We can look into one layer, see if something is there. If not, look down to another layer. If not, look on down to the other layer and so on. So we have this thing called the union file system. The union file system allows us to have files or content in different layers there, but still be able to see them from the container layer, for example, by looking down through that. That is a Linux functionality in there, to be able to search through the layers to find the content that we want, basically stacking the layers on top of each other and the files within that, but being able to treat it as a unified file system out there, even though it is made of multiple layers stacked on top of each other. One of the things then that comes to mind is how do we actually modify files? If we can't modify files in the image, if the layers are immutable, how do we actually go about modifying files that might be in those underlying layers in the images that we need to work with? The answer is one of the other things that is used in the Docker container process here, and that is the copy on write functionality. And the idea here is pretty straightforward, actually. It is that if I need to make a change to a file that is down deeper in the layers here, I can simply get that file, copy it up when I need to update it into the container layer. The container layer then has a copy of that file that can be modified. And because we have that union file system out there, we can still look through to the other layers. So when we need to actually make changes to things at lower layers in there that are immutable, we can simply get a copy of that via the copy on write functionality that brings it up to that top layer up there where we can make changes and stores a changed copy there. There are other Linux facilities like C groups for control groups and namespaces that help us keep our containers separated out. The idea with the container here is essentially that when we are working with it, we are carving out sets of resources on the operating system to be able to run in a protected space or in protected resources there. That to the application running within the container, it appears to have its own system, its own provisioned system or computer that it's running on there. But really what Docker is doing is carving out some of those resources in the operating system for purposes of running these containers. So the other nice thing about the way that we implement containers here is that because containers are based off an image and because that image is immutable, non-changing, and because a container is really only a thin read-write layer on top of that image, We can actually have multiple containers based on the same image. Each container can have the same underlying image out there because it is read-only, and then it can actually add its own read-write layer on top of it. And because the Union file system there, we can do this sort of looking through the layers out there. So the idea would be that we could actually have multiple containers that are using the same underlying image out there. They all have their own individual read-write layer out there. Think of it in the same way if I had multiple users, perhaps, or multiple users on the same computer. Each user can log on and has their own space to make changes in, their own space to do things in out there, but yet they're all utilizing the same underlying software stack out there, the same operating system and stuff. But each user has their own space that then is on top of the underlying provision software. Same idea with multiple containers out there. So the major difference again between a container and image is that top writable layer. All writes or updates go into that top writable layer out there, and multiple containers can share access to the same underlying image and yet have their own layer out there. So layers also simplify rebuilding or updating images, meaning that only layers that change need to be updated. If you think of the set of layers as making up all of the software in there, if you update software, for example, on a PC or a laptop out there, you don't redo everything. You update just that particular piece, that layer in there. So it's the same idea. As an example here, if we look on that right-hand side, you can see there's a command there, docker pull Debian. What this means is that we're using Docker to get the Debian image down, the image that would build the Debian OS out there or have a Debian OS in it. Notice that we pull down a couple of different layers out there, down, and then we have our image for that. Now notice then that we go down next underneath that and we pull Docker, a flavor of Debian called Jessie out there. But notice that it has, when it goes to pull the layers, the actual layers that it needs already exist locally. With Docker, the layers themselves that make up those, we said you can think of them almost like files to the OS, they are stored out there in var live Docker in the common case. Then we have then we would have the layers based on their hexadecimal IDs stored out in var live Docker out there and managed by storage drivers that Docker uses to manage the contents layers and the writable layer out there. So Docker has the layers stored out there. So then if we need a particular layer and we can verify that we already have that layer locally, we don't have to go and pull it again out of there. So how do we think about all this? We've talked about this analogy already quite a bit, but the analogy of installing software on a machine and then provisioning systems for users. But let's look at what this might look like sort of as a visualization. Suppose I have a new computer that I'm setting up, either perhaps as a something I need to do for my work or a family member out there. Typically what I would do is I would go through and I would install the operating system on it, maybe install some apps on it, such as the Microsoft Office apps, and maybe some virus scanning software or something out there too. The different layers of software. Those layers of software installed and provisioned there on that disk then form an image. That image can then be used to instantiate or stand up other systems. I can take that set of software provisioned out there and I can actually then copy it or install it onto another computer out there. In fact, then if I turn on that computer out there, it's like turning on and creating a container based off of the image. The image is always present in there, even when the machine is turned off. When I turn it on, if I've defined a user area out there, you can think of that user area as being like a read-write layer. That is an area for the user to make modifications and changes, and for changes to get pulled in. So we have that read-write layer kind of corresponding to like a user space or a user profile area on a computer out there. With that same image, I can also provision another system out there the same way. It gets the same set of software. The image is stored out there. When I turn it on and have that user area out there in a read-write manner, then I have the equivalent of like another container. So we can think about this in terms of a image of set of provision software defined out there, configured, can be considered like the Docker image. Then a Docker container would be each system where that image is used and where we have that rewrite layer out there. We're running the software out there. So just an analogy for you to use for that. If it's helpful to you, feel free to adopt it. If not, you feel free to find your own analogy or perhaps think in a way that makes more sense for you out there. So what is Docker in reality? Docker, again, from a marketing standpoint, is an open platform for distributed applications for developers and sysadmin. So basically, it's a way to manage containers. More specifically, though, Docker is this framework or this wrapper around it, a platform for using the underlying Linux technologies out there. We've mentioned these in passing already, the union file system, being able to look through the different layers and treat those different layers as the union of them, all of the pieces together. Namespaces out there for visibility, C groups for control groups. Again, the idea that what is happening here is when Docker is installed on a system, it then is managing these resources out there to give the containers their own set of resources carved out from the rest of the operating system resources out there. Docker also provides a RESTful interface for the service, a description format for containers, the API for orchestrating, for running containers, building containers, those kinds of things out there, and it provides a way to create the image by specifying the content and operations, the Docker file that it reads then and builds up the image from. How does Docker differ from a VM? We've alluded to this, but if you think about a VM as being a virtual machine, it requires a hypervisor and a guest OS to create the isolation. For example, I can run a Unix VM on a Windows system there, but I have to have the hypervisor, something like a VirtualBox, for example, or VMware out there, running on that system that then supports me installing the virtual machine on top of that and running things through there. In Docker, the approach is different. In Docker, the application Docker is installed on the system itself. There doesn't have to be this hypervisor in the mix there to run things on. Instead of relying on another program to run things out there, or the hypervisor to be the layer in between, what Docker does again is to think of it as carving out resources for a particular container area to run in there too, carving out some of the system resources using those Linux technologies that we talked about to give each container the appearance of having its own area out there to run with. Because Docker is working that way without having to have that hypervisor and the guest OS and all those pieces in there too, it's faster to start up. It's also more portable in being able to run an image unchanged in multiple environments. So what is a Docker file? Well, we've seen a couple of examples of these already. It's a way to create a Docker image, a plan for how we're going to construct an image that can ultimately be turned into a container. It's a text file that contains, in order, all of the instructions to build an image. Has a specific format and structure out there, and each instruction can create a read-only layer out there, or most of them can. Again, you can see on the right-hand side here a couple of examples, and you can see that on the upper one there, we're pulling down a version of Tomcat out there to support our web app. We have actually a web app that I built and we are passing it in. We're going to pass it in. Then we're going to copy that passed in web app over to this directory that runs in Tomcat and start up Tomcat via the Catalina SH. So that gets our web app that we built locally, pulls it in, starts it up and running. The database one on the bottom, we've seen this one a couple of times now. We start out with the basic MySQL image, database image out there that we can rely on to have most of the MySQL pieces and stuff that we need. We copy in some scripts that will help us to set up a database when the shell script that is the entry point is run there, and then we start at the MySQL daemon running. All of these things then, these would be the Docker files, the recipes for how we provision the image out there, how we get that software stack set up that we can then base containers off of. So Docker file to image to container. We have a Docker file on the left. We can do a Docker build to turn the Docker file into the image. We saw this in the animation I had where we played through this and saw it bringing down packages that it needed, bringing down layers that it needed, creating the intermediate containers along the way, giving those hexadecimal IDs and creating those layers and stacking them up in there based on the instructions in the Docker file. We then go to run it. If we run from an image there, we get that writable layer on top of that. Notice here that we had a set of layers in our image here that corresponded to some of the different things in there that we would be doing maybe in a Docker file. Not this, they'll be corresponding to the actions that we had, building up the layers for the image there, and then adding that read-writable layer on top to make it a container. And if we were to do a Docker history, then we would be able to see all the pieces that went into this particular image. Docker has a lot of commands out there. This is just a quick a snippet of some of them out there. We have the build command to take the Docker file and turn it into an image. We have the images command to look at the images available out there. RMI to remove an image, Docker inspect to give us some metadata back from the item out there. We can pull down code from a Docker registry with the pull command. We can give it a tag name out there, log in to a secure registry out there, push things out, and so on out there. You can see we can look at the ports, look at the history. We can also exec into it and get logs out. We'll talk about some more of these as we go along throughout the course here. So what does Docker run actually do for us? Basically, it pulls down the needed image. It checks to see if the image exists locally. In other words, you already have this image available locally, so I don't have to go out and get the pieces and build it again. If not, it's going to try to download it from the registry out there. And if it already exists on the local host, the Docker will just use it for the new container. So remember that run here is trying to create a container from the image. So we have to have the image available either locally already or by pulling it down from a registry out there. Then it will create a new container on it. When Docker has the image it needs, it creates a container by just putting a file system and mounting a read-write layer on it, creating a network interface, setting up an IP address, running any kind of applications or processes specified in there, and capturing, providing the output from the application there, making that available for us to look at as well. So what is a Docker registry? A Docker registry is simply a repository to store Docker images in. We can push or pull from it, much as you might think about pushing or pulling something like from a remote repository in the Git world out there. We can push images that we create up to Docker registry to be stored in there. We can pull images down from that registry to be stored out there. It can be public or it can be private. The public one is out there as Docker Hub, and then you can have private ones inside of an enterprise, inside of a company there, for example. It can also be secure or insecure, meaning that it can require authentication to get into, or it can be unauthenticated, insecure, open out there. The public Docker registry is the default one, hub.docker.com out there, which has a lot of the images out there that have been around for a long time, people contributing to them out there and so forth. We can also have these private registries. We talked about public or private. Private registries are typically hosted at some path or port inside of your company, or even maybe just running on your own machine if you just need a temporary one out there. But in order to work with anything but the public Docker registry, you do need to tag your images to add extra information to your images when they're created to say the port and the path that you are targeting out there to be able to get to your registry. So for example, if our registry, which runs at default at localhost colon 5000, we had it running out there and surfacing through localhost 5000 as far as URL, then our image would need to be tagged with localhost colon 5000 / the image name and not just the image name. Being able to have that information, the host, the path to get to it, and the port number out there as part of the image name tells Docker, if you are working with this, that it should reference the private registry as opposed to the public one. Without that kind of information in there, if you do a Docker push or pull, it will simply try to go out to the public Docker registry to get the image or to put the image up there. In the screenshot on the right-hand side of the slide, we have a set of repositories, a snapshot of the screen from the public Docker registry out there, hub.docker.com, and we have a set of Jenkins CI images that people can have made available and others can pull down and use. In this case, these are Jenkins continuous integration images, the Jenkins tool, things that can act as a worker node for the Jenkins tool out there. Variations of the various options here on these, but the idea is if I get one of these images down and then I spin it up, do a Docker run, start up as a container, this container can serve as a Jenkins worker would serve out there too. It can serve in that same capacity out there. It's just running in a container instead of on an actual physical machine out there in the same way we would normally have stuff installed and get it set up. Again, the image would be provisioned with all the pieces of software that we need to be successful here. It would be, for example, the base operating system image, Java versions out there, probably SSH or stuff, depending on the protocol to talk to it. And it would understand once it spins up and starts running, we start running it, how to talk back to the Jenkins master. That information could probably be passed in and configured via some environment variables, for example, that we might pass in to the container when starting this image up. Little bit quick note here about Docker tags. Docker tags are user-friendly aliases for the hex IDs of the generated images. We talked about and have seen that as we go through and create these layers in images, each one has a hexadecimal ID out there. It's in the newest version. It's like a 256-bit digest, they call it, checksum or hash out there for these IDs. And then if we don't want to have to reference them by the image IDs, and by the way, you can get away in most cases with only using maybe the first 4 or 5 significant characters of the image ID if you talk about the image IDs. But these are, we can use Docker tags to put human-friendly names on them. So these are human-friendly aliases for those hex IDs out there. They're a way of referring to an image similar to how you might have a git tag referring to a particular commit instead of having to reference it by the SHA-1 value if you're familiar with Git. 2 general ways to create a tag. We can do it at build time with Docker build. The -t option out there could give us a name to put on it as well as the tag portion. Now, tag is an overloaded term in the Docker tag vocabulary out there. Tag, it refers to the action you can do. Tag refers to the version part of it, the part after the colon in the name of the image out there. Or it can also refer to the larger part, which is the name and the version piece out there. So typically, you could do it via a Docker build. If I do a Docker build, you'll notice the -t here, the particular name of the image, and then the tag or the corresponding version number I want to have to reference this, and then the dot. The dot is simply the context, where to get the things, where to look, in this case, the current directory. So Docker build -t roar-dv v1. So I'm going to take it, in that case, it would take a Docker file. It would go through and create the layers out there and create an image that was ready to run this stuff that I needed for this roar-dv v1. Note that I'm tagging it here with a name followed by a version information number and then running it within that same context. The other way to do a Docker tag is via the actual tag command. And again, same sort of idea. I can take an image ID where an image ID might be that hexadecimal image ID. It also might be another tag itself out there. And I can add in the image name and a tag on it and give it a tag that way. Here's an example of that, taking a binary image out there, tagging it with a name and a version number to be usable out there. We can also note that we can also do things like tag an image, referencing it by its existing tag, its existing name, and tag it with a new one out there as well. Tagging for private registries. Private repositories run on a registry host. We talked about, for example, by default, the one that you get, the one if Docker registry, is just another Docker image that you can spin up and run as a container that implements that registry when it is running as a container. It acts like a Docker registry. For example, if it's running on localhost 5000 out there, then we would need to tag the image with that information. In other words, if we didn't add it at build time, we would need to go in with Docker tag and actually tag that image with that additional information about the host and port out there for that particular registry. Again, that's a way that tells Docker when we're working with it to get images in there that this should not try to go out to the public Docker registry out there, but rather to the one that represented by the information in the tag. For example, the one running on our localhost system on port 5000 here to get to act with that registry there. Now, one other note here, in Docker, there is the notion of a latest tag, meaning that portion after the name there that is can be referenced there instead of having a specific version number. There is a latest tag. The best advice with the latest tag is to simply avoid it because it doesn't mean what most people would think it means. It does not mean that it is the most recent image every time you reference one that has the latest tag on it. Rather, it simply means the default version that is added there if I don't give a specific tag. Meaning that if I were to not supply the v1 up there, for example, in roar-dv, when I was doing a tag, it would give me roardb:\latest. Okay, that was at the point in time I do that. It probably is the latest version of this image out there. So latest may make sense. But after that, if I do apply one and give specific tags, it is no longer the latest. It will still have latest on it as that tag because the time I tried to tag it, I did not give it that suffix in there, that supporting that suffix tag in there. But latest will not be the latest anymore. So latest is just a point in time default tag if I don't supply one. So latest, the best thing to do is probably avoid using latest and always try to use explicit tags, explicit versions out there when we actually tag something out there, because latest can get out of date very quickly, but the actual latest tag will apply to a version, whatever version it was on at the point in time that that image was created. So the trick again is to basically avoid it and use meaningful tags instead. So then the question becomes, how do we work with multiple containers? So we have this idea now of what a container is, that it's based off an image, it has that read-write layer out there for it, and it is based off of it. But most applications are not going to simply be a single container out there. They're going to be multiple containers. For example, the demo application that I'm using throughout this presentation has both a database piece and a web app piece. So I have a container for the web-based piece. I have a container for the database piece. When I start talking about trying to spin up multiple containers from different images and start trying to manage them, it can be challenging to do that and to get that thing managed easily out there. Fortunately, there are a couple of different ways we can actually manage that here. One of them is the Docker Compose tool. What Docker Compose does for us is it allows us to start containers together. It allows us to reference multiple images and the information about how they should be turned into containers in a Docker Compose.yaml file. YML is YAML format, yet another markup language. So we can specify in this Docker Compose file that which containers we need, and also what kind of things they need to pass in to work. What kind of information about which ports should be opened out there or exposed, what other ones it should link to, and so forth. Notice here on the right-hand side, my web app is referencing to my MySQL session out there. I'm a MySQL container. So we have multiple containers in the mix, and we can specify the relationships, we can specify the settings and stuff in a Docker Compose file, and then just run this Docker Compose up command to actually execute that and create the container from it. Note that Docker Compose, two words there, hyphenated actually when you run it, is not an actual Docker command. It is rather a tool out there, Docker-Compose, that you run to get this functionality out there. But certainly for just for a small set of containers, you could use Docker Compose to manage when you want to run them and how they work together and those kinds of things. So when composing containers together, essentially a three-step process. You create the Docker files for each part of the app. You define the services that make up the app in a Docker Compose file, and then you run Docker Compose up and it starts and runs your app. Another way to do it is through the Docker run. You could actually use a single Docker run command to manage multiple containers and link them together and so on. It works with the -- link option, which is an extended form of syntax out there. Note that they may be doing away with that link option at some point, and it gets to be quite complicated when I'm trying to, on a single command line, specify things about how multiple containers work together. This is why it becomes useful to have the Docker Compose file out there with that specification in it and use the Docker Compose tool to run that. There's also a Docker stack option out there. This is a fairly new one. They've incorporated Docker. It's a command in the Docker command line interface that lets you manage your cluster via Swarm. Swarm was one of the competitors to Kubernetes out there, and it also can leverage Docker Compose YAML file. The final way, the final way we're going to look at to work with multiple containers is through Kubernetes itself or through Kubernetes environments. This is part of the design goal of Kubernetes, is to be this orchestration or this overseer for sets of containers running out there. And it is the preferred way today as far as the best practices to be able to orchestrate and run and manage large sets of containers out there. The overall Docker flow, let's suppose in our host system there we have the OS, we have Docker install, we have an image out there. Docker images are stored in a registry. We talked about the public and private registries. A Docker file describes how to create a new image, just trying to give you kind of a quick visual reminder here of what we talked about. The Docker file then has a set of commands in it, can reach out and grab basic images out there, pull stuff in from our local systems out there, copy stuff in, run commands out there, and ultimately create containers for us. Containers, we can have multiple containers within our system here based on the images we define. And then a Docker Compose file that describes how to create containers and link multiple ones together. For example, how to take a compose YAML out there with two images, link them together, and start them up and running. One other point here as we're finishing out our containers topic here is to talk about the Open Container Initiative. So Docker has primarily been associated with containers as the main application that we've traditionally thought about as being able to create, manage, and run containers out there. However, it is not the only one. In fact, in time, some of Docker's, shall we say, the market share out there, there have been other competitors out there that can do similar kinds of things which are available to use. And so we have the Open Container Initiative, which simply is a way that Docker has been able to work with the Open Container Initiative part out there, the Linux Foundation out there, to create a specification and describe a way of doing things so that if you do these things and you follow these specifications out there and you follow the Open Container Initiatives, then you too can be like Docker. That is, if you have an application that can do the same kind of container formats out there or images or so on out there too, by following this Open Container Initiative and by being consistent with it, you can do the same kinds of things Docker does out there. So that has led to other players in container space, and some of these have actually been around for a long time. RKT or Rocket has been around for a long time. Podman, Builda are ways to develop containers out there. Cryo is about container runtime, and they're the same sort of thing. Runc, runtime for OS containers out there. So a number of different contenders that are available to you other than Docker. In fact, I think in more recent versions of like the Red Hat Enterprise Linux pieces out there, you won't even find Docker being included anymore. You will have a couple of these kinds of applications that are included and available to you to work with containers. But the same ideas and principles apply that we've talked about. It's just that they are implementing the Open Container Initiative so that they can act as you might expect Docker would in these situations. So next we'll talk about Kubernetes. So what is Kubernetes? Kubernetes is a portable, extensible platform for managing containerized workloads and services. A little bit of a mouthful there, but cluster orchestration system. It's designed to help manage all of the different containers out there that we have and all of the cluster in the Kubernetes environments out there. Frequently, it's abbreviated as KATES, K8S. It's derived from the Greek for helmsman. That's the icon, the ship's wheel out there. So KATES is the Kubernetes abbreviation, refers to the 8 characters that are between the K and the S, the first and last letter out there. This is becoming sort of a stylistic way to refer to these applications out there. It was formerly known as Borg, which is the internal Google project, open sourced by Google in 2014, and groups containers that make up an application into some logical Unix for easy management and discovery there. So it's about being able to manage these containers as sets in groups that belong together out there and making sure that it is a robust deployment out there, meaning that if something happens to a container, it can stop it and spin up another one out there. If it needs to scale up containers to handle a load, you can allow Kubernetes to do the scaling for you to add more containers out there and then to drop it back down. So especially if you're having to pay for cloud resources, for example, you can save some money there. So Kubernetes enables teams to work with these containerized workloads, multiple containers out there in a much easier manner than you would normally have to be able to do otherwise out there. Kubernetes features Has some features out there, service discovery, load balancing out there, being able to share things between containers. You don't need to worry with service discovery in most cases. It's going to take care of it for you. Kubernetes, or Kates here, gives pods their own IP addresses and a single DNS name for a set of pods. What is a pod? A pod is a construct that Kubernetes wraps around containers and any attached volumes to them. In Kubernetes, the pod is the lowest unit of granularity or things that we work with there. Pods wrap around containers. Kubernetes then manages pods. It can do automated rollouts and rollbacks. It can roll out updates to it. It can also monitor progress of things and to make sure that it can keep the system going there, keep instances of applications going in the containers in the pods, and it can automatically roll back changes for you as well out there. Kubernetes also deals with storage orchestration. You can automatically mount the storage system of your choice. So if you're working on a cloud, for example, in AWS, you can use S3 out there. The storage can be local on a cloud or from the network out there. So Kubernetes allows us to manage where we store our data. It also allows for batch execution out there and to make sure that any containers that fail are replaced out there. It is self-healing, replacing containers that die, replaces the rescheduled containers when the node dies off, in other words, the machine they're running on, and it can kill containers that don't respond to health checks. So if a container goes rogue and isn't responding to a standard check out there and threatens the health of the overall system, for example, or issue, then Kubernetes can kill that one off and spin up another instance of the container, again, based off of the image. It also supports secret and configuration management, that is, being able to hide or obfuscate sensitive information out there and what we call secrets. Configuration values like environment variables and stuff, we can store those as Kubernetes objects so that we don't have to rebuild images or expose things out there. Treat them as separate objects that can be managed by Kubernetes and define either the secret information or configuration information. It also supports horizontal scaling, automatically scaling up or down to have a certain level of CPU usage out there. So if we have more CPU usage going in there, we might add more containers to actually or lower them depending on what we need to do to get back to the desired level of CPU usage. It's a way of dynamically adjusting the number of these pods wrapped around containers, remember, to make sure we can handle load and to make sure we're not costing too much or running up resource bills here. Automatic bin packing. Kubernetes can automatically place containers based on resource requirements and constraints out there, meaning it can schedule them on the machines that are running Kubernetes in the best way to make as many fit on there as it can to be efficient about it in there, to make sure it can utilize the resources out there. So if we have multiple containers and they need a certain amount of resources. If Kubernetes can, when it actually is working with these, it can schedule them on the same system there to try kind of like a puzzle piece, getting the best fit for that machine out there based on the number of things, the containers and pods it's having to run. So what does Kates really do for you? Well, Kubernetes provides you with a framework to run distributed systems resiliently. It takes care of scaling requirements, failover deployment patterns out there. It's sort of like your virtual unattended deployment engineer out there, making sure that your deployments are up and running, making sure that they are able to service what's needed, making sure if there's a problem that it gets corrected out there, that kind of thing. When we talk about how to think about this, an analogy here with this that I like to use in terms of Kubernetes related containers, if we think of containers as being like those individual machines out there, we might think of like a data center as being analogous to Kubernetes. What do I mean by that? Then what is the main jobs of a data center out there? If you think about a data center you have at your work or perhaps is supporting you out of a cloud space somewhere, then the main jobs in data center are to provide systems to service certain needs, regardless of the applications. You want to be able to provide the applications running in containers out there that serve the needs the customer will have. Keep them up and running. If you think about a data center, when those computers out there, the ones that are supplied there for customers to use, want to keep them up and running. If something goes down, we get an alert or such, and we get information then sent back to us. So we have to go out there, the data center personnel, personnel, see what's wrong, and make sure that they update it. They go out and they do what needs to be done. It might even be replacing a system that's died with a new system out there. Add more systems, remove systems depending on the load. This is kind of like that scaling that we talked about. If we are a retail company, for example, we might add more computers in our data center to handle an increased load during the holidays out there. And then afterwards, we might remove them or scale back down because we don't need so many anymore. We don't have as many customers coming to our site, but we don't want to pay for the extra resources, the electricity, the other things that are being used, hardware for that. So we can actually, data center would be responsible for helping to scale up or scale down to meet load requirements. Deal with systems that are having problems. We talked about that. If we get an alert that a certain system is not functioning, we want to make sure we address that. And more often these days than not, it might mean just pulling that system out and replacing it with a different system there. Deploying new systems when needed, when we have a new business application, for example, that we want to work with, and we need some compute power to handle the website traffic we're going to get from it, we would have deploying some new systems out into the data center, perhaps dedicated to that, providing simple access to pools of systems. If you think about a data center operator actually monitoring sets of systems out there through a common terminal or that sort of thing, making sure of the systems are running, regardless of which system things are connected to out there, have kind of this virtual interface or overview of them out there. So in our sense there, Kubernetes is everywhere. It's effectively won the war versus the other competitors out there. Other competitors include things like Docker Swarm and Mesos you may have heard about. But the cloud providers all endorse it, provide ways to get a Kubernetes cluster out there. There is the Amazon EKS, Elastic Kubernetes Service. There is the Kubernetes Google Kubernetes Engine, GKE. There is the Azure Kubernetes Service, AKS. These are all ways that the cloud providers have for you to get a Kubernetes cluster to work with if you're using their cloud out there. As well, Kubernetes exists in certain implementations on enterprise platforms, things like an OpenShift out there. OpenShift is the Red Hat enterprise implementation of Kubernetes, has other functionality layer on top of it, but at its core, it's Kubernetes out there provided to run an enterprise with some convenience features provided by Red Hat. So let's talk about a little bit of terminology here. First off, what is a Kubernetes cluster? So the cluster is a set of machines, a set of typically of high availability computers that run Kubernetes on it. For example, it could be either virtual machines, actual physical machines out there, whatever the case may be. So the abstractions we have in Kubernetes allow us to deploy containers in the cluster without tying them to a specific host. What we mean by that is if we have multiple of these worker nodes out there where we could run things in these containers that are wrapped in pods, then we don't have to care about which system they end up on. That's Kubernetes' job to figure out how to run them. Just as it might be a data center operator's job to figure out where to put new computers in the data center, or where to tie them in, or which rack to put them on, and so forth in there. So Kubernetes automates distribution and scheduling containers across it in an efficient manner. And you'll see on the right-hand side here representation about how things may be laid out in Kubernetes, how things are laid out in Kubernetes in terms of the node. If we think of the whole thing as a set of cluster and the set of machines out there, each one being a node, then we can have a couple of types of nodes. The one is the master node, which is overseeing things for the worker nodes, helping with scheduling, those kinds of things out there, interfaces to users, APIs out there as well. That's the master node. Then you can have multiple worker nodes out there, which are responsible for actually running the pods, which ultimately have the containers inside of them. The nodes can be VMs or physical machines again, and the nodes will have a thing called a kubelet on them, the worker nodes, meaning that this is the Kubernetes agent software. We'll talk more about this in a moment. Let's take a look at what a cluster overview is here to help you get a basic idea of how a cluster is set up. So if we start out thinking about the master node here, the master node is set up to coordinate get input, that sort of thing out there. And then we have various worker nodes out there in our cluster as well. So the master node has an API server on it, which serves, as the name says, to serve up the API, provide API access to things in Kubernetes out there. It will also be interacted with through this command line interface called kubectl, kubectl. Now you'll hear it called kubectl. You may hear it called kubectl as in cuttle, or kubectl as in cuddle out there. Any of those are talking about the Kubernetes command line interface. The command line interface has a config file associated with it. The config file sets the environment that the command line is running in. So that also ties into and tells it which cluster it should be working with. So if you're using the command line, it needs to know which cluster it is supposed to send the things to and work with out there. That's essentially what the kubeconfig or the config file does for us out there. So a person working with this then might go through running kubectl on the command line to do some command for Kubernetes out there to get sent to the API server. The API server, if it needs to work with the workers out there, each worker has a program on it called kubelet. Think of that like the Kubernetes agent piece, the agent that runs on the worker node that allows it to talk back to the master and the API servers out there. The master will also have something called etcd on it. etcd is basically a key value store, keeping track of information out there. A controller manager. A controller in Kubernetes is a process that tries to ensure that the specification that you have provided for Kubernetes matches what you've actually got running in the cluster. It is trying to always reconcile the information you've given to Kubernetes with what's actually running in the cluster out there, the controller loop or the reconciliation loop out there. The scheduler is what schedules work, schedules pods. The pods contain the containers again, schedules the pods to run on the worker. The workers will also have something like Docker on them. They might have another one, but something that implements that that OCI specification that we talked about. Because ultimately, what we are running within Kubernetes is containers. Now, containers are created from an image. We have an image registry out there we've talked about. There's the public one, the Docker Hub, for example, or we can have the private ones we know of, like the local ones internally. When we go and create an image out there, get an image and create a container, those containers are housed in pods within Kubernetes. The pods then can be used or kept inside of the containers, kept inside of that pod. We can have multiple containers and any of the sorts of storage that they have attached out there is represented by the green disk here in this particular pod. We can have multiple pods on the nodes out there. In fact, we would expect to have multiple pods. Each pod can have multiple containers and their storage associated with them. Additionally, on the nodes, the worker nodes of the cluster, we would have the kube proxy out there. This is a proxy that allows someone to reach out and work with the node itself or talk to the worker nodes out there and to the processes running on them. We'll have more to say about how some of the ports and openings and stuff like that later on in the class. But the kube proxy allows the worker to talk with it. The final piece that really is a mainstay here of the overall cluster is the Container Network Interface, or CNI. This is the part that allows things in the cluster to talk to each other, the nodes and such, communicate through various rules and such, and manage the access to different things. But it's all about the network communication in there. These pieces are typically plugins that we have into Kubernetes, and they'll have fabric sort of base names. Things like Calico, Flannel, or Weave out there. You can see sort of the fabric theme in there. A networking interface fabric out there across the cluster to allow things to communicate. So that's our overview of the cluster out there. You can see there's a lot of parts, but none of them in this sort of at least kind of a block diagram form too complex, I think, to really understand or get a handle on here. You get the idea, though, that how it's structured. So some quick terminology here. We talked about some of this already. Pods are an object in Kubernetes that contain and manage one or more containers, any attached storage volumes they have. The service is an abstraction that groups together pods based on identifiers called labels. What we mean by that is a service. This is not a microservice. This is a Kubernetes service. When we are actually working with an application running in a container, we need to be able to access it through network information or something, sending traffic to it, getting things from it. That goes through the pods. Each pod will have its own unique IP address. We could connect up to each pod through its own unique IP address, but by definition, pods are meant to be able to be deleted and spun up again if needed out there. So if something happens in my pod and I need to delete it out there, I don't want to, when I get another pod back, it will likely have a different IP address. So I don't want to tie my connections to a specific pod IP. So a service gives me a virtual IP out there that I can connect to. And then on the back end, it will manage talking to one of the pods in the group there. So the service will figure out how to do the load balancing connection and stuff on the back end. All I do is connect to the service. The service takes care of then connecting me to a pod running in the background there. And so I don't have to worry about that. I just connect up to the service as an abstraction on the front end of a set of pods out there. A deployment defines a pod specification, but also defines something called a replica set or replicas. Replicas out there say how many of these pods should I have. This goes back to the idea of being able to deal with the load. I may just need one pod to handle the load of traffic coming in. I may need multiple ones. But the replica as part of the deployment allows us to specify how many of these things we need. An ingress is simply a resource that lets cluster traffic be exposed, or cluster applications be exposed to external traffic, and a namespace is simply a logical grouping of these different objects together so that we have a common way of grouping them together and referring to them. So how are containers organized on Kubernetes? Kubernetes clusters have nodes. We talked about that already, nodes out there. The nodes run the pods. The pods are wrapped around one or more containers out there. The pods are front-ended by a service to be able to access them. And the pods are scaled by deployments to see how many we need to have out there. And then namespaces within Kubernetes cluster group objects like pods, services, and deployments together. So the pod, again, is the smallest deployable unit in Kubernetes. We talk in Kubernetes terms, we're talking about pods, not containers. Pods wrap around the containers there. We represent a group or one or more containers, any shared resources, which we said it can be volumes or unique cluster IP addresses out there. Pods are scheduled on nodes automatically by the master, and but you can also specify a particular node to run on with a selector. A selector is simply an identifier, a label, a tag out there. We'll be talking more about selectors a little bit later on. Scheduling takes into account the node's resources, meaning just the scheduler is smart to figure out, will the thing I'm trying to schedule fit onto this node? Are there enough resources for it to be able to run successfully on it? Containers should only be scheduled together if they're tightly coupled and they need to share resources such as the disk. Two containers running in the same pod can actually talk to each other over localhost. They don't have to have any other way. They can talk to each other over localhost out there. So the pod will be scheduled and then run on a node. Namespaces, again, simply a unique working area within the cluster to kind of group things together, separate them out into logical units may consist of services, deployments, and so on out there. They provide a logical partition of the cluster's resources. Kubernetes resources are scoped to a namespace. The namespace becomes part of the way we reference them by the namespace they're in. All resources in a namespace must have unique names out there. Kubernetes allows for some quotas around that if we need them. The namespace, the default namespace in Kubernetes is, ironically enough, called default. That's the name of the namespace that we get by default out there. A namespace object is abbreviated NS. When we talk about objects in Kubernetes, they can all have ways of referring to themselves or referring to them. NS is the namespace. An option is -n if we're supplying it on the command line, for example, to reference a different one. We can set the context to change the current one out there if we wanted to make it instead of default, to say the default one is called foo, for example, or some other namespace. What is kubectl? We've mentioned kubectl already. It's a command line interface for out there. It has a kubeconfig file associated with it to tell it which cluster to work against, any kind of necessary configuration information out there. The command describes an operation to do on one or more resources, such as a git, describe, log, create. These are all Kubernetes commands. Most of them we'll talk about throughout the course. It has a type that it can take. So we talk about the command we want it to do or thing. the type of object we want it to operate against. For example, we want to operate against a pod, a deployment, a service out there. And then the name is the name of that particular resource. For example, if we're working with a pod, we give it the pod name. Out there, if we're working with the deployment, we give it a deployment name. So we're running a command, an operation, against a particular type of object designated by one of those built-in types, pod, deployment, service, so on out there, and then the actual name of the object, and then any flags, optional flags for the command. Some example kubectl commands, kubectl get. Think of that as a list. That's what I tell people. Think of that as a list out there. Get me a list of these things. Get basic information about the set of objects out there. Kubectl apply. We'll talk more about this as we go along, but Kubernetes is based off the idea for configuring it of being able to use these YAML files that describe how many deployments we need and what they look like, how many pods we need and what they should look like, and that sort of thing. When we have these specifications out there, to get them actually to happen in the Kubernetes cluster, we use the apply command. The apply command says, take my specification from the YAML file and make one of these in the cluster for me. Make it happen in the cluster for me. So apply is basically saying take the specification and execute the specification to create the things I need in the cluster itself. Kubectl create, similar idea. Typically, though, you're not using a YAML file for that. You would be using create a type of object for maybe a create an NS, a namespace called foo out there, kind of a short method of that. Kubectl describe to get detailed information about the current state of an object, or kubectl delete to delete an object out there. So you can basically get the idea here of the kinds of things we can do from the command line. Speaking of YAML, YAML is a type of markup language, defines Kubernetes specs for resources. It's stored typically as .yaml or YML text files out there. Kubectl apply takes such a file's input, updates cluster objects based on the specs, turns the YAML specs into resources in the cluster. If you have something running in the cluster and you want to be able to get the YAML that's used for it to create it out there, you can dump that out with kubectl get-o YAML. Basically, think of it as list the resources out there in a YAML format. What is YAML out there? Again, you may already be familiar with this, but it's a human-readable data serialization language, typically used for configuration files. Big word for just saying it's a way to organize information or data into a specification that makes sense for computers or for things like Kubernetes and applications to use. Usually has an extension of .yml or .yaml, YAML meaning yet another markup language. It is space and character sensitive, used by a lot of applications, particularly in the Docker, Kubernetes, Helm, those sorts of worlds out there. So on the right-hand side, you can see one of these YAML files here that defines some things for Kubernetes. In this case, we're defining an object called a persistent volume. A persistent volume refers to a persistent storage out there, a volume storage out there. In other words, storage that doesn't go away even if the container and the pod go away out there. It's still persisted. There's an API version in there for the version of the API we're using with this, then some metadata, such as name and labels we can put in there, specifications about the particular items we want. For example, we're talking about storage here, so you can see we're talking about a capacity, access modes, the path to it, and so on. Then a persistent volume claim is a way of saying, let me get access to that storage. So again, same sort of pattern, API version, the kind of objects, some metadata out there, names, labels, and then information about what characteristics we want this to have. So YAML file here, note the indentation here, the way that we can identify which things are associated with which other things at a higher level by the indentation here as we go down through it. So that becomes very important in there. So what do you need to know about YAML really? Well, a couple quick things. The conventional block format, if you're denoting a new item in a list, uses the hyphen and a space out there, as you can see at the top on the right-hand side there. Keys are separated from values by a colon and a space out there. Indented blocks use indentation to separate key value pairs. So we have key and value out there. We separate them, indentation and new lines out there for the different items. Strings do not generally require quotation marks. Data structure hierarchy is maintained by the outline indentation. What that means is the more you indent, the lower in the hierarchy it is. So starting like from the left side, as that's high level, you would indent a little bit to get the second layer, indent a little bit more to get the third layer, and so on down the line. So let's talk about understanding some Kubernetes objects here. To work with Kubernetes objects, you use the Kubernetes API, or you can use the Kubernetes command line, but basically you're using the API either way. The kubectl command line tool makes calls to the API for you. You could also use the Kubernetes API directly through the Kubernetes API client libraries if you didn't want to go through the command line, if you wanted to write your own programmatic interface to Kubernetes. Kubernetes objects are persistent entities in the Kubernetes system, meaning that they are persisting out there based on the description, the way they should be in the YAML file. Kubernetes uses these entities to represent the state of the cluster. They can describe, for example, what application containers are running on which nodes out there, what resources are available to them, and policies around how these applications behave. A Kubernetes object, you can think of it as a record of intent, meaning this is what I want to have when it is in place in the Kubernetes system. It's declarative. Instead of telling Kubernetes how to create it, you're telling it, as in being imperative, you're declaring what you want, and Kubernetes' job then is to make that happen. After creation, Kubernetes will work to ensure the object exists. And creating an object declares you want the cluster, what you want it to look like. It's known as the desired state. It's meaning that you're telling Kubernetes what you want out there instead of how to get it. It's a declarative model versus the imperative model. So a little bit more about this to kind of get it fixed in your mind. Kubernetes is a desired state system. The user supplies that desired state, be it declaring it in manifest or YAML files out there. Kubernetes then works to balance the current state and the requested state. So it's trying to take what you've asked for in those YAML files and make sure that it happens and is set up and running in the Kubernetes cluster out there. So desired state is what you want your production environment to be like. The current observed state is the current status of your environment. If you look at the illustration here on the page, we might have a user have a Kubernetes specification, the YAML files out here. The Kubernetes user could do a kubectl apply, for example, and provide that specification into Kubernetes. Kubernetes then, through things like the controller, would run a reconciliation loop to say, you've specified you want two of these, you want a service, you want a deployment, whatever the case may be, and get those up and running in the cluster out there. So it would take what you specified, get it running in the cluster, and go from there. When we define a Kubernetes object in here, we talked a little bit about this, but let's look just a little closer at what we have here. So when we define an object in Kubernetes, we have to provide an object specification to get the described desired state out there, a basic info such as a name, perhaps the tags, and so in there. The Kubernetes API expects info as JSON in the body of the request, but usually you simply provide it with YAML, and the kubectl command line converts it to JSON for you. JSON is JavaScript object notation, a pretty typical way of being able to specify information to computers out there to applications. So if we look at the specification on the right-hand side, what we get, we see the field there. There's an API version. Which version of the Kubernetes API is being used to create the object? This helps us ensure that we're referencing a version of Kubernetes that can support what we need out there, especially if it's something fairly new out there. You may need to specify a newer API version that you can run against or use out there. We have the kind, what kind of object to create? Is it a deployment? Is it just a pod definition? Is it a service or so on in there? And then we have metadata about the object in there. Typically, this would be things like the name we want to assign it in the system and the label, perhaps, that we're using to select it or search for it in the system or look for it out there. You can even be, though, a namespace that we want to run it in. Remember that a namespace in Kubernetes is simply a way to group objects together with a common name and a common scope there. The object spec in there is going to be different for every Kubernetes object. We have a set of required fields, Then we have the object spec in there with specifications about for the type of object we're wanting to work with. It can contain nested fields specific to the object, and you can find more details on the specs in the API reference. Let's take a moment and take a look at the specification on the right-hand side of this slide. We have the API version at the top. We have the kind of object out there. We have the metadata about it, the name we're assigning it, the labels out there, the name, the labels that we are providing, as in a name equals value, the name equals war web. We could also have bar equals foo. It's just a way of assigning an identifier to it. We also have the namespace we want to run it in. And then notice that underneath those first common areas of the required fields, we have the spec area. The spec area would be where I define the attributes or characteristics about the specific object that I'm working with. In this case, we are talking about the top right, a deployment. That is a deployment object. Remember that a deployment is used to both define a pod and also to define the number of replicas or number of instances we want Kubernetes to keep around for us. So here we have the number of replicas at 1, meaning that we always want to have one of these running. If something happens to that one, then because we've set up a deployment here that says we have to have one, Kubernetes would go and spin up another one there. Then notice that we have some metadata about it, some more labels in there for the replica piece in there. Then we have another spec. So again, the deployment has both the number of things we want and then the pod specs itself. So the second spec there, it's indented further, is about how do we create the pod. The first one is how to recreate the replicas that we need. The second one is how to create that actual pod. So the container in there we have for that pod, Aurora Web is the name, an image. So this is the container image. This is the Docker image. This is how we get that container to go inside this pod. We tell it an image. Then what happens is Kubernetes is pulling the image down, going and running it, creating a container, putting it in the pod, and so on in there. We could also have information that's particular to the kind of application we're trying to run in the container. In this case, ports out there that we're going to expose within the container to make sure we get information in or out. Then notice that there's a three dashes there. That is a separator. You can have multiple specifications in the same file, separated by these three dashes out there. We have, again, the same required fields as we did for deployment, the API version, the kind of object, the metadata. Metadata, again, having things like names or selectors as labels out there and namespaces. And then note that the spec looks a little bit different. We have a certain type of service out there. We need to tell what type of service. We have the ports we want to expose as well out there. So ways to specify the Kubernetes objects in these YAML files. Now, when we actually have these YAML files, these objects we put into Kubernetes, and Kubernetes has taken this and has actually spun them up and is running them out there, then we have additional information that Kubernetes provides, both this, not just the spec, but also status information. We still have the original spec out there, the way we defined it to get it into Kubernetes, but then we also have the status. Status information says, this is what Kubernetes, this is the state of the object, this is the status of the object. You can see over there under the status on the right-hand side, all this information about the last time it did this, or the last transaction time, last probe time, those kinds of things. Information about the object, information about the most recent things it's been doing or been done to it out there, providing the actual state. If you're wondering how I got this, this is from a kubectl edit. In other words, a Kubernetes command line being able to edit the object in place. You can actually edit it in place and then modify things. You could also get the information, dump it out with the -o YAML for that format and get information there. The -n at the top of this command is for the namespace called roar2. We're asking for the pod object. Remember we talked about the Kubernetes format. Typically has the command is edit here. Any kind of flags, you can use the flags out of order here a little bit, or in wherever they fit into command line -n, the namespace. Then we have the type of object, the pod, and the actual pod name, the name of the object in the system there. So updating resources in place. If we want to update something in place, an object out there, ideally what we would really do is we would go back and modify the YAML files and then put a new one of these out there. However, since we've already been talking about it a little bit, I'll tell you that there is a kubectl edit command here that can be used to edit a running object out in the Kubernetes system in the cluster. Basically, we're editing its YAML definition or its definition on the fly here. So we can say kubectl edit the resource type, deployment, service, whatever, and the resource name. And then basically this would give us a way to actually bring up that object in an editor for us. We can configure the editor out there with the kube editor variable. Then we can go in, edit the thing, make changes that we need to, save it. When we save it, Kubernetes will validate whether or not it is syntactically correct. If it's not, it'll throw you back into the editor instead of saving and exiting in there. Now note that the change, this is a on-demand type of change on an instance of the running object. It is not persisted back to the original configuration source. So if you were to go back and apply the original YAMLs, you would still get the original specification, not anything that you've made change as far as edit. You could also restart an object out there if you needed to. Selectors or labels. Selectors and labels are used throughout Kubernetes. This is the idea of human readable identifiers and ways to identify things. Labels are mechanisms that we use to organize Kubernetes objects to basically allow Kubernetes to tell which sets of things it should be working with for particular situations, but also to allow us to find sets of things that we were interested in. A label in Kubernetes is actually a key value pair without any predefined meaning. It's like a two-part, the part before the colon, the part after. The part before is the key, the part after is the value. So we can have the label here. If you look on the circle, the red circle here on the right-hand side of the slide, you can see that we have a label here, env development. Think of it as the environment is equal to the development environment. Now, if we want to look at the labels on different things, we can again do the Kubernetes command line. Note that we have the command followed by the type of object, followed by flags in this case. We don't have a particular object we're looking at, but we're telling it to show the labels. If we did that, we would be able to see the label out here, the environment equals development label here on the actual object out there. We can also add a label to an object with kubectl label command. Kubectl label pods out there would give us the ability then to apply a particular label to it for environment equals, or the owner equals Michael in this case out there. And so then if we look at the labels again, we would see both the previous label, environment equals development, and owner equals Michael out there. Selectors or labels, we talk about labels as an identifier. They're also used as selectors, ways to pick and choose particular object within Kubernetes. So you can see here, I can do things from the command line like get the pods where the particular label is one of these sets. This is kind of set selection here, set based in a particular set. So most Kubernetes objects support set-based selectors, choosing which items based on a set to select from. What's an example of this? In Kubernetes, it might be you have a service which has this virtual IP you can connect to, and it needs to know the set of pods that it has a choice to connect to on the back end. The way it identifies those sets of pods is by a label that is used in there. I'll show you an example of this later on. But basically, the pods would have a label on them, and then using that label, the service could select which pods it could actually work with out there. For the option to search these or look at these or to use the label, -L is the short form, -- selector is the long form. So in the first example there on the left-hand screenshot, you can see we have kubectl get pods -L, env in production or development, which simply means give me the list of pods in whatever namespace I'm in here, the default namespace, that are either in the production environment or development environment, env in production or development, meaning that the env key can have one of those two values out there. Other commands can also use label kubectl delete pods. I can delete the pods associated with a particular one by using a -L out there. You can see over in the top right-hand side, I can select them based on a particular label if I want out there, get the pods out there. So the labels provide a way to select specific objects within Kubernetes or to get objects matching a common attribute out there, those kinds of things. Another example I've used before when I'm working with Kubernetes is, for example, we had nodes in the cluster that we needed to have one node that was had more resources, significantly more resources on it to run more intense things on it there. So we added a node and we gave it a lot more disk space out there. And I added a label that said, like size equals biggest out there. So I know which one we could then use and specify that size biggest when we needed to run something that needed more resources out there. So labels can apply to other objects such as nodes and services. You can have equality-based selections out there, equal, not equal to, or set-based ones as we've seen here. The kubectl command line syntax, the takeaway from this is the syntax can be in a couple of different forms. We're talking about the objects here. We've already talked about this idea of having the command, the type of object, the flags, and so on in there. What we want to point out here is if you look on the right-hand side, kubectl get service -n roar2, what that is saying is list out the Kubernetes services that are in this namespace -n roar2. And you see that we have the MySQL and the Roar Web ones out there. We can also just do the get services out there to get a list of all of them in the second example there. But then notice on the bottom part of the layer, the last example, kubectl get -n roar2 grep service. If I am just saying get the list of services out there or get the list of objects, get all the objects out there, the all means get all the objects. Then if I was only interested in services, I would have to grep those or look for them. Notice here too that when I say get all the objects, the name of the object in there, that service MySQL, service RoarDB, the type precedes the object name. Okay, so service is the type, MySQL is the object name, service is the type, Roar Web is the object name. So when we can talk about these things in Kubernetes to identify an object, we're typically talking about a type of object, a name of an object in there, and perhaps a namespace. But the name and type can be specified separately or together in this kind of form like you see in the last line here. So we can do kubectl in -n get all to get all of the things in there, or kubectl get all -n. Notice that we can swap the flags around in different locations here on the command line. We can use different forms of the resource names. We can use single, plural, or abbreviations. Objects in Kubernetes will have these three variations. They'll have a singular form, such as pod, a plural form, such as pods, an abbreviation such as PO out there. And abbreviations exist for most of the resources. PO for pod, SVC for service, deploy for deployment, etc. out there. So a deployment can be thought of as a supervisor for pods. That is, it's actually putting the pod in place out there, creating it. Once it's deployed, you can see the deployment, the replica set, and the pods out there. So if I have a deployment out there, let's say I have a deployment that specifies a certain type of pod, it specifies two replicas out there. You see on the right-hand side, the Kubernetes specification out there, the API version, the kind, the metadata, in there with the name in there, and then the spec. Remember that for a deployment spec, we specify both the replicas, how many of these things we want, and information about that. And then we also specify within that spec the actual things we want to run in our pod, in our containers. Again, things like the image out there, the container port that are exposed, environment variables, that kind of thing. So deployment can be thought of as a supervisor for pods. Once it's deployed, you can see the deployment, the replica set, and the pods. So if I were to apply this manifest, this YAML file out there, then I could go and say Kubernetes get or list out the deployments you know about. You could say, okay, I've got this deployment out there. How many I've got? We're up to date. I can say get the replica set or replicas out there. It'll say I've got 2 of those. And then it say get the pods associated with that. Now, one other thing to notice, if you look on that little screenshot here on the left-hand side, notice the naming here. Our top level item, the deployment, has SISE deploy. Our replica set here has SISE deploy and then some random number on it. And then our pods have SIS deploy with the random number, that is the replica set, and then another identifier, random identifier after that. Why do we have these numbers and why do we have these random identifiers? Because objects within a namespace within Kubernetes cannot have the same name. So they have to have different names associated with them. So they'll have different names associated with them out there to separate them out within the namespace. So the names of the pods are derived from the replica sets. The names of replica sets are derived from the deployment. So what happens if we make a significant change? We update a version number or some piece in there, for example, within the deployment spec, and then apply it. Then what happens is Kubernetes is smart enough to understand, oh, I've gotten a new specification for this. I should get rid of the old one that is based on the old specification, and I should go out and then update it. So it will terminate the ones that are currently running based on the old specification, spin up new ones that are running based on the new specification out here. So this is kind of cool. This is an easy way to do updates out there. So you can have a new version of your pod or deployment out there, service, change it in the specification, apply it in there, and if the change is significant, then Kubernetes will go off, get rid of the old ones, and actually go back and spin up new ones based on the new thing out there. Kind of like an update. This also, though, demonstrates the idea that the objects you have in Kubernetes are designed to be stateless. What do we mean by that? We mean that if the object can be killed off, if it crashes or has a problem with it, it should be able to be stopped and then have a new one started and pick up where the old one left off. That is, the object has to be stateless, not depending on the existence of the object to maintain its state. It might be writing out state information to disk. It might be such that it can matter. But think of it as like a database, for example. If I have a database running in a pod or access to a database out there, I don't want to store my database data in the pod itself because if something happens to that pod and it goes away, I lose my data. So I might write the data out to an external disk out there, a persistent volume. Then if something happens to my pod that's running my database engine, Kubernetes can kill it off, spin up a new one, and the new one can be conditioned or know how to go out and read the data and pick up again. So when you're working in Kubernetes, and absent of something like an operator to do custom processing, you want the applications, the things you're working with, to be stateless, to not be dependent on the existence of a particular instance to be able to succeed or fail, but just to be able to be killed off and started again if needed. Deployments versus pods. Let's talk a little bit about what that means. So deployments versus pods here. Suppose that I, as a user, am working with a pod out there. I have an thing. We know that objects run within a node and a namespace, a Kubernetes node and namespace out there. We have a user going through the Kubernetes command line, the kubectl, and we have a specification here, a specification for a pod. We're just doing a pod, not a deployment here. Again, the pod specifying the things that we need for our containers, the ports we need to show on, some metadata. But notice again, that same sort of outline of the same sort of structure in the file. The API version, the kind, the metadata, name, labels, and so on out there. If we take that specification, apply it through the kubectl command line, put it out into our namespace out there, then Kubernetes helpfully gives us a pod based on that. It will have a port that's showing up out there, and we can connect directly to that pod if we know how to connect up to that IP address to that pod on that port. The user can then do work out there. If the user is doing work out there and the pod goes away, then what happens? Well, then we have to go and manually start a new one. There's no deployment to handle this for us, nothing to do. We have to go and manually start a new deployment out, a new pod out there ourselves. So the pod goes away, we have to go and do an apply again, start up a new pod, and then we have that pod out there, but chances are we will have a different IP address on the new one, so we will not be able to connect to it. If we have a deployment, deployment has to include both a replica set and a pod. The replica set or replicas here mean that a certain number of these must be kept running and active at all times. So let's see how that would look differently. I have again my namespace out there within my Kubernetes cluster. I take this specification, I apply it out there, create a deployment. The deployment goes to that and says I have to have one of these running all the time, one replica. So it starts up a pod running for me that I can connect to there and access. What happens if the pod goes away? It has a problem in the container out there, for example. If the pod goes away, then my connection is broken, but the replica set within the deployment will automatically start up a new one because it says you're supposed to have one of these all the time, and now I see you have 0. So let me make sure I give you 1 to be consistent with the specification you put in there. So it gets us another pod up and running, exposing the port out there, and I can connect to it. Now note again that it wouldn't be the same IP address in all likelihood out there, so I still would have to figure that out, but I did not have to go through the manual process of creating a new pod out there myself. I was able to have the deployment take care of that because the deployment understood that I always wanted at least one of these running at all times. Services, as we've mentioned before, services Kubernetes provide a level of abstraction for pods. Pods can be volatile. We just talked about the idea, something might cause a pod to go away. And by the way, in Kubernetes, it doesn't have to be that a pod container crashes out there. It could be, for example, that a container, an application running container, has a problem where it starts chewing up all the memory on the system, and it starts consuming, it has a bug, and it starts consuming all the memory. Kubernetes will do whatever it can to try to protect the system overall and to try to ensure that as much stuff can keep running as possible. So Kubernetes can actually go out there, detect that that system is trying to use that pod, is trying to use too much system memory, the system is in danger, and it can kill off the pod. There's a certain algorithm it uses to try to figure out which ones to kill off, but your pod can be killed off by that. So we don't want to depend on pods always being around. Again, this idea that applications should be stateless. They should be able to be stopped, go away, start up another instance, and pick up where it left off. So a service in Kubernetes provides a level of abstraction for pods. Because pods can be volatile, you can't rely on the respective IP addresses to connect to out there. So the service provides this virtual consistent IP to connect to for a set of pods. Pods can be selected by labels. So think again of a service as being this kind of front-end abstraction out there that provides this not a real IP, but a virtual IP, and then on the back end decides which pod to talk to. That way, if something goes down, I'm not affected by it. I'm just still talking to the service out there. It exists to forward traffic to one or more pods. There's a kube proxy process running on the nodes that helps it understand which pods it can talk to, the service can talk to. There are kube proxy queries, the API server, to learn about new services out there. So let's look at an example of that and how that might look in our diagram. Suppose that we have our setup out there. We have a deployment which has 2 pods in it because the replicas are 2 out there. We always have to have 2 running. As a user, I can connect to individual pods if I'm allowed. If I can find out the IP address of that and I have permissions, I can go and connect to one of those and talk to that one over that IP address. I can do my work with it. If the deployment and the pod goes away, we lose access to that pod, but we know the replica set will detect that, or the Kubernetes will detect that, and because we've told it we need to have 2, it will start up another one to ensure we have 2 running. Now again, that other one will not have the same IP address out there as the previous one. So if I go to try to connect to that with the same IP address as I was previously using, I won't succeed. I'll have a problem with that, and so I won't be able to do my work. I can discover, go out and investigate and find the IP address that I need. I can even connect up to the other one and still do work that way. But if a pod becomes unusable, if it gets into a state where it's not responding, for example, it may not have crashed, but it may not be responding either, or it may be stuck in some kind of a situation where it goes away and is using up memory, those kinds of things out there. Then if it becomes unusable, then the Kubernetes can kill it off to protect the system. And so you can have other pods that can handle the needs, but there's no way to automatically discover or connect. You still have to manually do it. So let's say we have the same situation, but we put a service in front of it. And here's the specification for the service out there. You'll note again the same kind of structure, the API version, the kind, the metadata, the name, the labels on there to allow us to select it, the namespace, and so on. Then notice we have a node port service here, or for the type. The node port in there means that I have a port open on the Kubernetes node that I can get to things through. We'll talk in a moment about the different kinds of services that are available to you to use, but node port means that I have a service on there to use. I also have the port and target port out there as well, which is referring to the port in the service I'm talking to and the port in the container that I'm talking to as well. So notice also here that I have a selector out there for web. So the service provides a virtual address on to connect to, and then it talks on the back end to the particular, you can choose which one on the back end to talk to. The endpoints, we talk about the idea of endpoints in Kubernetes. Endpoints simply mean the IP addresses of the set of things I can connect to, the service can connect to. So in this case, the endpoints, it figures out which services, which pods it can connect to based off of the selector. Note if you look closely in the diagram here, both of the pods wrapping around the containers have this label attached to them that says name equals roar web. Then the selector or the label that we're looking for is name equal roar web. And if we pull the IP addresses or get the IP address for both of those become our endpoints for the service. The service knows it can talk to any of the endpoints there that have that selector out there that match up there. So for our point, we have the IP addresses out there. If we then want to talk to the service, we have to get to the node first through the node port. Then we have to get to the services port and then the target port on the actual application itself. You think about the idea of pods running an application. The application or the container may expose a port there, and the containers running in these pods can expose the same port. You just pick the one you want to talk to out there. That allows us to distribute the load, for example, coming into a set of pods out there. So if we're doing a node IP, there is an open port on the node itself. Typically, it's in the range of like, I think it's around the 30,000, 31,000s in there. And basically, when we talk to that, you can see the green arrows here. We talk to the node IP. We can then go through that based on the specification to get to the 8089 port, which is the port of the service. And then we can get through that to talk to an open port on one of the pods, whichever one the service routes us to behind the scenes. So the cool thing about this now, if one pod goes down and becomes unavailable, the service can then connect up to the other pod on our behalf. Note that I'm not affected. I'm still talking to the node out there, so I don't care that the pod has actually gone down. I can still go through and the service will route me to another pod on the back end, even while the replica as part of the deployment says you've got to have two, you're down to one, I'll spin up another one for you, make it available for you, and then both of them are available again. But note that I didn't have to set up another pod myself. I didn't have to go investigate which IP address I could talk to now of another service out there. I simply could go through the service, and the service was up all the time because it's just a virtual IP address. And on the back end, the service was able to select a pool of pods it could talk to based on the selector. And then I'll get back to two. The same condition if the service becomes unavailable out there. If the pod becomes unavailable, same situation. The service can switch on the back end to another pod and keep me up and running. Types of services. There are several types of services we could work with within Kubernetes. There's called the cluster IP service. This is basically the default service. It's intended mostly for use inside the cluster, for apps to talk to each other inside the cluster. There's no external access really except via a kubectl proxy. You can see there inside the cluster, we have that internal traffic that goes through the service port that then goes through on the back end to the pods. There is a node port. We just talked about that one, the idea of having a port open on the Kubernetes node itself that we can get in and talk to. Then traffic is sent to the actual service port and then to the ports on the pods. This will use the node IP address to connect to. And then the ports will be in the range, the node port itself will be in the range 30,000 to 32,767. The load balancing service is what you would typically find if you're using like a cloud environment out there. Puts a load balancer object out there in front of that with a single IP that forwards all traffic to the service. Default method for directly exposing a service out there on like a cloud environment or such, no filtering, no routing, but there's a cost factor associated with it on the clouds. Finally, there is also an external name service. I didn't illustrate that here, but it maps the service to the contents of an external name field like foobar.com, gives you a CNAME record with that value to work with for there. So going back to our data center analogy for Kubernetes, we can think of the Docker containers as being similar to the computers in a rack. Think of the containers and the volumes out there as being similar. Think of the containers themselves as being similar to a computer in a rack. I think that's what I said. Think of the set of containers out there in a pod being similar to a rack of machines out there, having multiple machines in it. And then replicas as being kind of like multiple racks out there, and a service as being like a central control for a login service to get to the back end to a set of things out there. And then on the namespace, similar to a server room out there containing all these different types of objects. Let's talk a moment about some other Kubernetes objects here. If we finish up the basics, config maps and secrets. So we have a couple of approaches. Any object that we work with out there is going to need some kind of configuration. It might be simply environment variables or some option or whatever out there. We need some kind of configuration. And for it's an alternative for hard coding data or using environment variables. We can, within the pod spec, set environment variables, set hard coded values in there. We could do that. We could also, inside of a Docker file or inside of the Kubernetes YAML file out there. But the bad part of that then is that that's going to be hard coded, tied to a particular container or deployment. And if we need to change them, we'd have to go back and modify the specification for that container and redo the deployment. So the data also has to be duplicated across objects. So a better way to manage this then is to separate out those settings, those configuration values, into what's called a config map. A config map is a Kubernetes object then that contains a configuration value and setting out there, or multiple of them. And then you separate that out from the pods out there, from deployments and so on. And then you make that available for them to use. So they can read information out of that config map. Multiple objects can use that and get that information. You don't have to duplicate it across objects in terms of specifying and specification. You don't have to redo the deployments to actually update it. You can just change the config map itself. A secret in Kubernetes is a lot like that. It's just a matter of an object that's out there that's designed to obfuscate or hide the information that's sensitive information, like passwords or API keys or so on. Unfortunately, with the secrets, the default is really just a base 64 encoding, so it doesn't do that much. It hides it from plain text, but it's very easy to crack or reverse engineer out there. If you really want to be secure with secrets and stuff in Kubernetes, you would really want to use something like a Vault. Vault is an application from HashiCorp that is actually useful for storing this kind of information out there and managing it for you. So secrets are in config maps are similar, except that secrets have this base 64 encoding by default to obfuscate or hide the information so it's not in plain text out there. Let's take a look if we want to actually create examples of these. Suppose we had a spec on the right-hand side. We have a container out there called environment test, and note that it has a API key in it and a language. If I wanted to go the config map route and the secret route on this, I would break that information out. Instead of having it hard coded in here, I would actually create a secret, for example, with the API key. And you can see we're using the kubectl create command there to create this object that's of secret type, the type of object out there, an API key, and from literal, the information you want to store in there. And then we could also specify it in a config map for the language. The same idea, create a config map that has this information stored in there. So in this way, we can specify it out there through config maps out there. Once we actually update these or create these, then we would need to update the spec to use those. So we've changed it from being hard-coded in our spec, but now we need to make sure we change the thing that was using these or needed these values to reference the objects we created. So note that from the top to the bottom there, on the bottom, we've changed it to have an environment variable, the environment variable language, to get the value from a config map key ref. In other words, a config map we created out there, the name of the config map, and the value we're looking for in it, or the key. Likewise, the API key, we've changed that to get the value from this secret out there called API key, and to look for the value in it called API key. So we take the hard-coded values, the config maps, the secrets, those kinds of things, break them out into their own object in Kubernetes, and then change the objects, the other objects that need them to use the new objects out there. That's the basic workflow. Persistence, volumes, and claims out there. Persistence has to do with storing data about information on disk out there. The trick here is that if we were just to store things in the container itself, then that's considered ephemeral, meaning if the container goes away, we lose the information, okay? Think about it from the standpoint if you had like a container that was like a laptop or a standalone computer. If I destroy that computer and that's the only place I have the data, I've lost the data associated with that. Same idea with the container. We've already talked a lot about containers within Kubernetes being thought of as stateless and being they can go away, they can be killed off, and the new one started up. So we have that container, and we don't want to store them with the container. When we have the container going away, then if that we would lose the information. So another approach here is to store it as a separate volume. That is a volume defined within the pod level storage there, which is great. If the container goes away, we still have the information stored within the pod. But if the pod goes away, then we lose the information in there. So if a deletion of the pod is going to delete the volume out there. So we really want to store the information somewhere outside of the pod, outside of the container. And in Kubernetes, we have an object for that called a persistent volume. It means that it has persistent storage independent of the life cycle of any pod. And to get that storage, then you actually issue a persistent volume claim. A persistent volume claim is a way in Kubernetes of requesting a set of storage or a kind of storage out there, getting a claim to it. It defines the specific amount of storage requested. It defines specific access modes out there. And what Kubernetes does is it looks to find a persistent volume and match it to the claim out there. So over on the right-hand side, if you look at the printouts or the listings there, you can see that we have a persistent volume claim, which says that I want to have read access, read write access out there, read write once access. I need something that is a storage of 128 meg, a certain storage class out there that I need, and I need the name of it need to match up with this Redis stuff out there. If you look at we have a deployment then we're specifying out there. Note that down further in the deployment, over on the right-hand side, we have in our container spec, volume mounts, how do we get to the data, volumes, the place to look for the data, and a persistent volume claim out there that's Redis PVC, which says, this is the persistent volume claim object I want you to look for, and give me storage that matches what it asks for out there. Okay, so this is the way that objects in Kubernetes can ask for different kinds of storage. You have a persistent volume, which can be a particular type of storage available to you on whatever environment you have, an object for that, and then a persistent volume claim, which means that an object can put in a claim to request that sort of storage out there. PVCs have a different access modes. Read-write once, one bound pod with read-write access, many bound pods for read-only access, read-only many out there, read-write many, or many pods with read-write access out there. So again, persistent volumes are resources in the cluster. They are the physical volumes on the host machine that store your persistent data, the actual storage you're using out there. The PVCs are the request for these, or that's like claim checks to get to the resource you want. It's a way of telling the platform, telling Kubernetes what kind of storage you want and what kinds you need, as defined in persistent volumes out there. Persistent volumes get attached to your pod via the persistent volume claims. So you can think of the chain here as being that a pod has a request, a PVC, persistent volume claim, to get a certain type of persistent volumes. Persistent volumes then are defined by storage classes out there and exist on some host system out there. Storage classes help us define the type of PVCs that a user can request. So we talk about storage classes out there. Then storage classes will have a required provisioner via the volume plugins or via volume plugins in the system. You can see here the kinds of volume plugins we're talking about, and you can tell from the names and such the kinds of storage that they are tied to. For example, Azure files for Azure stuff in the Azure cloud out there, AWS for the Amazon Web Services out there, Elastic pieces out there. You can also see the iSCSI, some of the more common ones there, NFS, local, and so on there. Storage classes provide a way for admins to describe the classes of storage they can provide and also to describe the characteristics for those different kinds of storage out there. Things like quality of service level, backup policies, other custom policies out there. The storage class is also going to contain information about the provisioner, any kind of parameters associated with it, the reclaim policy, those kinds of things out there. So this will all be used in persistent volume. The class needs to be dynamically provisioned. Admins can specify default storage classes out there so that if you request a persistent volume claim, that you'll get a certain default out there if you don't override that. You can see on the right-hand side there some example of the storage class and different parameters that it has. Let's next talk about resource requests and limits. Requests and limits are mechanisms that Kubernetes uses to control resources like memory and CPU. I usually tell people to think of requests as the minimum and limits as the maximums out there. Requests are what the container is guaranteed to get. It's what we are saying we have to be able to run successfully within the system out there. Kubernetes is going to be smart and only schedule containers on a node that it can meet the request, or actually scheduling pods, we should say, out there. So think of it this way. If we're saying we need a certain amount of storage, a certain amount of memory, a certain amount of CPU out there, then for all of the things that Kubernetes is looking at trying to schedule out there, the sum of all those requests still needs to be less than or equal to the resources available on the node where it's trying to schedule. Limits defined upper bounds for us. Again, why we say think about limits as a max out there. Container is only allowed to go up to the limit. If it hits the limit, it's going to be dealt with. And we'll talk about what that means in a moment, how the system reacts to actually things that are going over the limit or threaten to consume all the system resources out there. Specifying the resource request and limits is a best practice because it allows the Kubernetes scheduler to make better decisions about where to put pods. So you can have memory limits in there measured in bytes. These can be expressed as either bytes, fixed point integers out there, or this megabytes, which is a power of 2 equivalent out there. CPU limits can be measured as units, usually as a CPU core, and we can talk about them in terms of things like millicores out there. It can be fractional, as in a pod with a CPU limit of 0.5 is allowed 2 times the power of 1 limited to 0.25 out there. In our example, we have 100 millicores, so 100 out of 1,000 there, so a tenth of a CPU core out there to work with. So again, a megabyte is just a multiple of byte, but expressed as a power of 2 out there. So how pods or resource requests are scheduled. When you create a pod, the Kubernetes schedule is going to select a node for it to run on out there. Remember, the scheduler had that part of the Kubernetes of the cluster master out there. We talked about having a schedule on it to decide how to schedule things on the nodes. Each node has a maximum capacity for resources, memory and CPU out there. And the scheduler is responsible for ensuring that for each resource type, the sum total of all the things it's trying to put on there and the pods, containers being scheduled is less than the capacity of the node. So it's making sure again that everything fits, that it does this intelligent scheduling where it doesn't overburden or overrun the resources available on the node. The scheduler sticks to the request and won't schedule if the request is more than the node. So even if the actual resource usage is low, if the request that has been specified across all the things you're trying to be scheduled on there is more than the node can tolerate or more than the node has, things won't get scheduled. So you can sometimes end up in a case where there's not enough resources available on any node to actually schedule the particular item out there. That's why it's important to try to be as clear and as accurate as you can with the requests and when you're putting them into the pods out there for the systems. The request being, again, the minimum you need to work with out there. So what happens when we do pass resource limits? We have actually start to overrun these resources that we have available on a particular node. So if a container or pod with a container in it exceeds its memory limit, it may be terminated. If that container is restartable, Kubernetes will restart it for you. This is again alluding to that idea that anything that you're running within the Kubernetes system there should ideally be restartable, able to pick up where it left off, even if it gets killed off. This is another example. Think of the Kubernetes again as that data center model we talked about. One of the jobs of a data center model is to make sure that things can get that we have enough system resources out there to run our stuff. And if something gets out of hand, starts using too much resources, we may remove that system and in terms of a data center out there and replace it with another one, or even just kick it and restart it, reboot it out there. So if a container exceeds its memory requested, the pod will likely be evicted when the node runs out of memory. So the badly behaved pod is punished out there. So that means that if it's exceeding the memory requested, it can be evicted by Kubernetes, kicked out there, so that it's no longer running in the system. Container may or may not be allowed to exceed its CPU usage for extended periods of time. It's less, the system is usually less strict about if a container or pod with containers is exceeding the CPU usage out there, because it understands that sometimes that does spike up or not out there. So containers don't get killed off for excessive CPU usage. The kubelet, the primary node agent that we talked about, that kubelet that runs as an agent on each of the worker nodes out there, handles these kind of issues with error conditions out there since it's on the node. The kubelet's main job, or one of its main jobs, is to preserve stability when the node resources get low, to make sure that it is keeping the node healthy, to make sure that the node doesn't get over loaded with different things, consuming too much resources out there. So the kubelet has the ability to evict one or more of the pods to reclaim system resources if things start getting too intense in terms of consuming the memory out there, the CPU, those sorts of things. When the pod is failed by the kubelet, the terminates all the containers running inside the pod, and kubelet makes the eviction decisions, though, based off of signals it gets about the resource and certain eviction thresholds out there. So node conditions indicate the state of the resources. You can get these conditions reported sometimes, or reported in the output about certain pods, or in there about pods. If they're exceeding disk, they may have, if the node is running low on disk, you may get the disk pressure alert out there. If it's exceeding the memory requirements, you may have the memory pressure warning out there. So then alerts on these can be triggered by eviction signals. If pressure conditions are triggered out there, it tries to discourage the scheduler from scheduling more pods on the node. Basically, the idea is if it's already detecting that it's overloaded, it doesn't want to schedule additional things out there running on the node to load it down more. The killer, this is an interesting term you may hear at some point working with Kubernetes. Is OOM, out of memory. It's a special handler to help deal with the system out of memory event that happens before the kubelet can reclaim memory. Basically, what happens here is kubelet sets an OOM score for each container based on the quality of service for the pod. If the gets called into action, it calculates its own score based on the pod score and how much memory pod is using. The container with the highest score then, as calculated through this process, gets killed off out there. The intent here is that containers with the lowest quality of service using the highest memory should be killed first to reclaim the memory. What that means is basically if it is not a very important container out there, if it doesn't have to be up all the time, if it is not important or significant in terms of staying up all the time and having high quality of service, and it starts using the highest memory, the idea is the system will kill off the lowest important containers out there that are chewing up the most memory in an attempt to provide more memory for the ones that do need to be a higher quality of service and are more important out there. Health checks. In addition to the health of the system, Kubernetes is concerned with the health of the pods out there. So ideally, pods should have health checks built into them as a best practice. We have both a readiness probe out there, which allows the kubelet to assess if a service is ready to start accepting traffic, in order for a pod to be considered ready, all of its pods are ready. So can this stuff accept traffic, traffic coming into it? Is it ready to respond to it and receive it out there? The liveness probe allows kubelet to monitor and assess when to restart a container. Think of it almost like we might call it like a heartbeat or something out there. It's a liveness probe that we can at least be checking, know that our pod is responding to things, responding to the signals we're sending to it, and that it is still alive. And if we don't get that liveness probe isn't getting out there, then kubelet will know that it probably needs to go out and restart this. 3 kinds of health checks can be included in either of these probes. HTTP health checks, the kubelet will call a webhook. If it returns between 200 and 399, it's considered success. Otherwise, it's failure. Container exec, the kubelet will execute a command inside your container. If it exits with status 0, it's considered a success out there. And there's also TCP sockets. The kubelet will attempt to open a socket to your container. If you can establish a connection, the container is considered healthy. If it can't, it's considered a failure. And you can see over there on the right-hand side for this pod, we're specifying a liveness probe there for the container, which is the TCP socket 1 on the port on there, an initial delay to give it time to actually spin up, and then a timeout to say if it doesn't respond this time, we need to try again. All right, let's talk next about Helm. So what is Helm? Helm is a orchestration tool for Kubernetes. That's one way to think about it. Kind of like a Yum or apt, but for Kubernetes out there, a package manager sort of thing out there. Bundles related manifests such as deployment YAML, service YAMLs, etc. into a chart. These kinds of things that we talked about for Kubernetes in the course, that is deployment services, all those different kinds of Kubernetes objects out there that we can put together into a single chart where they're grouped together to apply as a unit. When installing the chart, Helm creates a release. So we take a chart with all these different kinds of YAML files and manifest in there. We deploy it out there and then creates a release running in Helm. It has lifecycle management out there that it can do as well to create, install, upgrade, rollback, delete, give status, do versioning, those kinds of things in there. The benefits it also provides are templating, repeatability, reliability, multiple environment, ease of collaboration. So we'll talk about some of these things as we go along in the course here. But the basic idea of why we need something like this, if you think about what we've looked at so far, we have the ideas that we have different files to specify the services we want to have, different files to specify the deployments, different files to specify whatever it might be, ingresses or something out there, secrets, config maps out there. All of those are YAML files. Those can be difficult to edit, lots of duplication in them, and can be hard to overwrite. And so as we get, especially as we get more and more pods out there within our system, more and more services, more and more deployments, it can be tricky to manage all of those and be able to keep up with all the changes and what you need to put in specific YAML files. So instead, what you can use Helm. Helm helps to simplify this kind of management for us. The Helm components out there, and I should mention here, we're talking about what was active in Helm 2. Helm 3 is out as of now. Overall, the functionality is still basically the same, but the implementation is different, and we'll talk about there's no longer any tiller. We'll talk about why there's not a tiller here in a moment. But the Helm client is a command line client, and in version 2 of that, it interacted with a tiller component or server that was inside the cluster, and allowed us to do local chart development out there, work with that. The tiller server was in the cluster, listened to the Helm client, interacted with the Kubernetes API, and managed the lifecycle. So it basically took the place of like if you had the command line client from Kubernetes out there talking to things in there. Tiller is the server piece for the Helm client out there. Tiller sits inside of the cluster to act with against the Kubernetes API to make the changes specified in the chart there. Helm charts are a collection of Kubernetes resource definitions files inside a directory. At the top level is just the directory, but you can see on the right-hand side here has several different components in here. You can deploy simple and complex applications. Most files in a chart can be templated. What we mean by that is that it has a placeholder to substitute in actual values. It's a template out there. You can actually substitute in different values. That allows us to do things like reuse out there. Reuse one of these templated deployment files or service files out there and fill in the values that we want for that and to have everything else be the same. It uses a variation of the Go templates. If you know Go, the programming language, or know of it, there's a set of things called Sprig out there, but it uses a variation of the Go templates in there in Helm. The values to instantiate in templates come from this file called value YAMLs out there. You'll see values YAMLs over on the right-hand side as being one of the top-level files out there. And then underneath there, we have a set of templates. Those names should look more familiar, things like deployment.yaml, ingress.yaml, service.yaml, and so on. So those are the actual specifications for the Kubernetes objects that we want to create, but they'll be templated with placeholders where we want to put in actual values. And the actual values, with the help of Helm, can come from the values.yaml file or from the Helm command line override out there. There's also a helpers TPL file, which is a helper template file that can define different functions out there based on actually kind of programming that we can do, a sort of programming we can do for different functions to return values to be put into the YAML files. And then you can have a directories of chart directories out there. So a chart is a package, a bundle of Kubernetes resources. A release is a chart instance loaded into Helm. Same chart can be installed several times in there. Each chart will have its own release. And a repository is a repository of published charts out there. A template is simply a Kubernetes configuration file set up as a template. Helm operations, a set of operations we can do out there. Helm init, which simply goes to install tiller to running cluster and sets up any necessary local configuration. Helm create allows us to create a new chart. Helm delete is basically given a release name. Remember that a release is a running instance of something deployed in the cluster by Helm. Delete the release from Kubernetes. There's a -- purge option to remove the release completely. There is a Helm install to install a chart. A Helm lint to make sure that you check a chart for issues out there. Helm list lists a set of releases of the charts that are installed in a cluster. Helm rollback to roll back a release to previous version. Helm status, checking on the status. Helm template to render the template. In other words, plug in the values and dump out what that template looks like with values plugged in there, but don't actually apply it to the cluster. And Helm upgrade a release out there. So all these kinds of different options and commands out there around dealing with charts, making sure things look good, dealing with releases in the cluster. Again, once you have a chart, specifies all the pieces you need for the full set of objects for something running on Kubernetes. And then when you're running it on the chart there, when you put the chart into the cluster, then you have a release out there. And then at that point, you can list the releases, roll back to releases, do upgrades, and so on out there. But again, you're able to manage that set of things running in the cluster as a unit, as a release using Helm, just as you're able to manage the set of manifest files for all different things using a chart. Helm charts are based off of that they're allowed to have templates in them, but templating based off the Go templating language, as we mentioned. Template directives look for values, insert them. The template directives looks like the opening and closing braces there, a couple of them, 2 on each side there. The values passed in can be thought of as a namespace where a dot represents each element. Take a look at the right-hand side of this chart to get a better idea for it. So here we have a values file. We'll pretend that it has in the YAML format, a key value pair, favorite drink is coffee. Then we have our template file out there. And if you look closely at our template file, It's a config map here. You'll see the things that look very similar, just like a regular Kubernetes object. We have the API version, the V1 out there, the kind config map, some metadata about it, some data values to go into it. But note that we also have these areas, these sections enclosed in this opening and closing, these pairs of opening and closing brackets out there. And that we have these .release.name, .values, .favorite drink out there. So the open and closing pairs of brackets there simply mean this is a place where values can get plugged in. This is the template here. This file, this template file, has places to substitute in actual values. Some values will be computed for you automatically. For example, the release name will be defined based on what you have in the chart out there. So no .release.name. Think of the dot, it's just kind of separating it from a section point of view or a level or a hierarchy. So that the top dot there is starting at the highest. We go into the release section, release level, and then we get the name value out of that. When we talk about the drink one there in the second screenshot there on that page, you see drink, you see .values, .favorite drink. So the .values here represents coming from the values file or getting passed in, and then the .favorite drink is the key we're looking for in there. So that if I do this thing of Helm install down below on the third screenshot here, Helm install -- dry run -- debug my chart. The dry run and debug are basically just saying don't actually apply this in the cluster, just show me what it looked like. You can see that towards the bottom there, it actually took the template file, plugged in the values that we had there, plugged in the release name, which again was generated for us from based on the chart. And then for the data value there, the drink in there was substituted in with the value from the values file. That .values favorite drink means go out to the values file, find the favorite drink key out there and substitute the associated value with it, in this case coffee. So the leading dots and the dots in between indicate a hierarchy out there as well. Again, certain items are built in. You can do dry runs to see rendered versions of the templates out there, what they look like with values plugged into them. So Helm charts, again, one of the key values here, or one of the key things they provide, is being able to override values easily there. So it's not only being able to plug in values from a values YAML file, but also being able to override it on the command line. For example, if you needed to run through multiple charts to install multiple things, you could differentiate them just by supplying different overrides on the command line or a different value YAMLs file, and then you could deal with multiple ones more easily without having to duplicate or hard code all the things in there as you would without Helm. So overrides can come from child charts out there, additional values files, or command line values. If you use the -- set option on the command line, that's going to have a higher precedence than the values YAML file. So that's how you can override things in the command line, because it takes a precedent over what we have in the values YAML file. The values can also be structured in there, means like the dot notation to indicate the hierarchy. Lower scoping requires more levels in there. As you get down further and further, you add more dots to it to separate it out there. So we talk about Helm charts on the right-hand side there. Note that we're installing, you have a dry run debug. Again, this is just the try it without actually applying the cluster, but note the one there that says -- set favorite drink equals slurm. And then we actually then when we run that, instead of getting the thing in our values file, we will actually get the substitution of what we supplied on the command line with that -- set option out there. You can also use functions and pipelines in our templates in Helm. That meaning that we can define the values out there in the values file, but we also have ways with the functions to transform data in a way to make them more useful, to do things like repeating them multiple times, putting them in quotes, even adding numbers to initial starts there and other numbers there, that sort of thing. Lots of different functions that we can actually leverage from the Sprig libraries out there. So functions transform data values in a way to make them more useful. For example, if we have a quote function out there, note that we could quote the thing that we'll be substituting in there. We call the quote function and pass it an argument. Helm has over 60 built-in functions from the Go template language or the Sprig templates out there. And pipelines in this case, we're not talking about delivery pipelines or deployment pipelines and those kinds of things. We're talking about chaining functions together. So if you look on the example on the right-hand side, we have our values file with the favorite in there with the key favorite section with the key of drink. The favorite drink is coffee. The favorite food is pizza out there. Our templates file says that we are going to plug in for the key drink, the value we get out of our values file. So we have it as values favorite drink. Again, looking at that hierarchy in the values file. Values on the front, dot values means going to the values definitions, dot favorite from the favorite section there, and then getting the value associated with the key drink. Then notice after that we pipe that through function to repeat 5 times and then to quote it for us. On the food part, we actually do something similar, except we pipe it through an uppercasing function, and then we quote it after that. So we actually rendered this, then if we actually ran through this, did a dry run, or actually ran it through and applied it with the installing a chart there, the values file would get, or the template file would get rendered as my value hello world, the thing we already had up there, the literal, plus the drink. Notice coffee, 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 coffee out there, repeating it 5 times, and then food is pizza, all in uppercase out there. You can also do nice things like you can actually have functions that would add an offset to a starting value. I've used that in the past when I was trying to work with multiple items in containers in there in a particular thing I wanted to deploy Kubernetes, but I wanted them to each have different ports they started with or different ports they were talking to. And I wanted the initial starting port to be relative so that I can install multiple instances of these things, and I'll just have to press specify starting port, and each of the items inside would figure out a starting port based on their particular offset. So I was able to pass in a starting port via the command line and have a Helm function in there that would actually add a preset offset for each type of object in there. That way I could actually install multiple charts from the command line and specify a different starting port for each one, and be assured that then within that they would add the appropriate offset, and I wouldn't have port conflicts or be reusing the same port. I didn't have to go through and hard code anything either, because I could use Helm to actually compute that for me for each one. Now, one of the things that about Helm 2, one of the reasons primarily why Helm 3 exists these days, or is as important as it is because of tiller is considered evil. What I mean by that is the tiller piece of the Helm command line versus in tiller there. Tiller is the server piece that lives inside the Kubernetes cluster. When it was first put out there, when they first started using Helm, Kubernetes was not secured in the ways that it is now. We'll talk about the RBAC, role-based access control permissions, a little later on in class. So Tiller is out there listening to the Helm client, interacting with the Kubernetes API, but the problem is that the way Tiller's been set up, it has too many permissions. Too much access is required. Too much access is a security risk. It's hard to secure because it was done before this whole RBAC thing. So it's been removed in Helm 3 because it's caused quite a bit of angst over being in the cluster and having that kind of access out there. In Helm 3, they removed it. However, in Helm 2, there's a simple workaround. You can simply do a Helm template command to render the different template files filled in with the values that you supply in the values YAML or supply from the command line, and then just pipe that through a kubectl apply. So basically you're just dumping out the completed YAML files with the substituted values in, and then running it through a kubectl apply, and that way you don't need tiller in there. Now, if you don't use tiller, though, in that sense with Helm 2, then you do lose the ability to do things like the upgrades, like the rollbacks, all those kinds of things, because you're not really dealing with releases in the same way that you would be if tiller were in the mix there. So Helm charts and subcharts, the most basic way of using Helm is to have a single chart. For a single application, the single chart can contain all the resources needed for an application out there. You can also, though, have a chart with dependencies to other charts, an umbrella chart, as you can see by the right hand on the right hand of the slide there. Other charts can be external. You can leverage requirements YAML file. You can also get away with a simple hierarchy if it's all local out there. Meaning if you just have a one service, one deployment, those kind of simple cases, you can just put them in a directory structure that will be understood out there and just use it that way. Helm versioning. Helm charts have their own version, which is separate from the application version. So this is contained in the Helm metadata out there, in the kind of top level area where we define charts. Has an app version, the version of the application, the chart, and has a version of the chart itself. So Helm, we talk about the versions of the Helm objects, the Helm charts, and then the versions of the things they're deploying out there with the Kubernetes pieces. So the simplest versioning scheme, we were trying to figure out a versioning scheme there, is just to keep the chart version in sync with the application. That is, every time you make a new version of the application's chart, you update the chart version out there as well, and just don't use the app version. The advanced versioning scheme is to use, if changes happening in the chart all the time, you want to track separately within the application, you can change the different pieces of it out there, do independent Helm versioning as shown in the right-hand side. Helm packages and repository. Helm charts can be worked with in two forms, either a packaged form, a version chart archive as a TGZ file, or a tree of files. If you just have a tree of files, you can check them into a Git repository, for example. You don't have to use a Helm repository out there. You can use it if you want. It's geared towards Helm to store package repositories. Works with the Helm repo or Helm repository command. And you get an index file, the metadata file for the chart package out there that's generated through this Helm repo index out there. Helm repo adds to store the chart in it, Helm fetch to get the chart down. And there's also an open source one called Chart Museum that can help you host Helm charts out there. So this is all about the commands to get things stored in a repository. Think of it like a project for a Git, for example. You take the commit for Git, put it up there, and you can do a git fetch or git pull or those kinds of things to get code down. Same kind of ideas. You're managing your Helm charts within a repository there. So quick couple of examples of what the different items do here. Helm initialize cluster installs tiller, sets up any necessary configuration out there. You can see by the picture we're doing a Helm init, installing the pod out there. Installing a chart, Helm install a chart, which puts it out there and then deploys the various pieces out into the cluster. Upgrading a chart, Helm upgrade, the release that you want to go to. So each chart has, or the charts when you install them, have a release in there. So you upgrade the release, you can upgrade pieces of it. For example, in this diagram, we go and tell Tiller to talk to the API server and to update the deployment out there. Next, we'll talk about Kustomize. So when we talk about working with all the YAML files and such that we use to configure Kubernetes and that we apply to it to get this kinds of objects we want in our cluster, those Kubernetes YAML files are often reused. There are several approaches for reuse out there. We can modify the original one to suit our needs. We can make multiple copies and edit them separately for different needs. So we can take one that works for us, go in and tweak it out there to have the values in that we want to set up in our cluster. We can make additional copies over there and keep multiple copies around in there to keep and to use. But the challenges with this is that we have a divergence from the original source files. The original ones aren't necessarily there anymore in their same form. They may have a copy somewhere, but we've modified them now for that. And having multiple disparate copies means it's more challenging to leverage a common base set. If I'm having separate copies out there, I can't necessarily get some kind of reuse out of a core set of stuff out there. I have my own copies I have to keep up to date. You have to make consistent changes across multiple independent copies for new versions out there. And so yet another approach is parameterizing templates, the kinds of things we saw with Helm out there, plugging in those kinds of information out there. The challenges with Helm are that templates and value files are not usable Kubernetes specifications, meaning that those files with the placeholders out there, the kinds of things we have in a Helm chart out there, we can't just take that and apply it. They have the placeholders in them, they have the function calls in it out there. They're more like a new kind of programming out there that wraps around the Kubernetes spec. Parameterized templates change the original specification. So they modify the original stuff we have out there. And many things become parameters for many different users. So you start building up this kind of overhead with Helm that you have of trying to have a sort of programming around the spec out there, trying to have the placeholders. It can get very complex very quickly, and it can be challenging then to do things even like making sense out of a simple YAML file, trying to read through it and trying to keep it all, and there was too many parameters out there. So this counters a typical goal of reuse, which is to keep differences between specs small and simple. Although it can be simple, depending if you're just changing a few things out there, it can get very complex as well. So another option that's come on the scene is Kustomize with a K. Kustomize creates with a K creates modified Kubernetes manifests by overlaying the specifications on top of existing ones out there. It allows you to define things that are overlaid, kind of like the union file system that we saw early on talking about containers, where we talked about having the layers in there, layering on these type of things on top of other files. So changes to make an overlay are out there stored in a separate file called customization.yaml, again with a K. Kustomize reads the customization YAML file and the Kubernetes spec files and dumps out completed resources standard out with the changes from the customization YAML applied on top of the standard Kubernetes files. Again, think of it almost like that layering that we described in a container image before, where we have the different pieces layered on top of each other. And the Kustomize build command, causes files to be processed and the output created. The output in this case would be the resulting YAML that we would feed into kubectl apply for the cluster out there, which would be starting with our base images or our base specifications out there, and then the overlays on top of those. Simple example here. Let's suppose we have a directory out here, a couple of directories, a little application I use, a deploy and a service out there, and a customization.yaml. So the web one has a set of things in it, deployment out there for our app. The service is a simple service definition out there. The customization YAML has some common things to put on it. So Kustomize has some keywords out there, some terms it uses, common labels, as you might guess, a common label to apply across a set of things, and a list of resource files that it's going to read, modify and emit as a YAML string. So it's going to read those files that we have out there. With the common label criteria there, note that when we actually do a customized build, what we get out the other side here is a set of YAML, just as we might expect for to feed into Kubernetes, which would have things on there. Notice that the service and deployment now both have this label here, level test, which was a common label applied from the customization YAML out there. That's a very simple case, but you get the idea. We can describe within the customization.yaml what we want to have end up in there, but note that we didn't have to modify either of the original files out there. We simply added something on top of them or layered it on top of them. Common changes you can do through Kustomize. Common label adds a common label. It's a name value to each Kubernetes resource. Common annotations adds an annotation to all Kubernetes resources. Name prefix adds a common prefix to all the resource names out there. Here you can see common annotations out there. If I do a customized build, then I get the build, latest, and branch master out there. Notice I get those annotations added into my Kubernetes object there. Likewise, if I had a name prefix, note that I have the prefix, the name attached in there onto my different objects. Variance is a common use case is needing multiple variations or variants of a set of common resources, dev, stage, prod, for example, out there. To do this, Kustomize has the concept of overlays and bases. Both represented via customization YAML file, including resources and customizations. Resources meaning the things that I read in, the original files out there. The customizations, the things that I'm doing to them to update them. So the base declares things the variants have in common, the common starting point, the common set of files we want to start with. The overlays declare the differences. Variants can also apply patches. Patching is a way to update the stuff, and so to add something new or to modify it slightly in there. A bit more than just adding something brand new out there, but actually modifying something existing out there. Partial deployment spec to update some existing spec as opposed to adding new information. It adds a new change to that, but it's actually working against an existing object in there. So let's look at an example here. Suppose that if I go out to my directory here, I have a set of things for the web app and a database of an application I'm working with. I have deployment service specs for both out there. I have a customization YAML out there in each one, and then I have a customization YAML at the top level and a namespace out there. So I have the resources for the database. The deployment simply looks like a deployment out there with information about the things I need to run my MySQL database. The service represents the service out there, the things need to run for that. The customization YAML then represents the changes that I want to make. So notice here it pulls in my underlying YAML files. Changes then uses a patch operation then to change the name from this RoarDB to MySQL. So it'll work as expected, assuming that we need the service to be named MySQL instead of the original item here. And notice the patch feature here. It's pretty easy to understand. Starting at line 11 there, we have the operation, the kind of patch we're doing. We're replacing things. We're looking for a particular path in the file and out there and value in there in our target and our RoarDB service file. I'll show you how that works more in just a moment. And we have the resources to include, the patch operation in there to define the patch to make to the existing text. The type of patch, as we said, the location in the hierarchy and the replacement value, how to find it, and the item to search for out there. Then we have our service definition. So if we were to actually do the Kustomize build against this, think of it as going out for the patch functionality here, looking for this particular object, the service object, service definition out there, finding the name of the object out there that matches what we had in our patch. We're identifying the one we want to modify. And then we have the path. So we find the path, the hierarchy within the specification there, within the manifest, the metadata name. And we want to find the name object, and then we want to replace it with that value. So then the YAML we get out from the other end has that actual, if we actually do the customized build, has that actual item in there replaced with that name. So the customized base is the original custom resources plus the customization here. We have the original resources in here. Looking at this, the web deployment out there, the web service out there, the list of resources files we're going to read in, the resources to include, and then if we do a customized build, we get that set of things out the other side. The namespace in there is the namespace. It's just an item to create, allow us to create a namespace fairly easily out there. Customization YAML at the top level then sets some common labels, also includes the resources that we have, the lower level directories in there. So add a common label in the metadata, and we have the resources that we include relative and absolute path out there to them. Do customized build, we'll get the expected things out there from just running through those directories, pulling in the resources, applying any kind of customizations that we have in customization YAML. Now let's talk a little bit about how some special functionality or ways that Kustomize helps us with config maps and secrets out there. So if we have the YAML defined on the left-hand side, we can define things traditional config map and secrets. We talked about this in the Kubernetes portion of the class. We can have it generate a basic config map out there. And remember, a config map is simply mapping sort of a key value pair out there to something. So in this case, we're creating a config map object for Kubernetes. We have the metadata out there as a name, then we have the data that we want to use. We can include this via the resources spec. So if we have it down there, we see the resources we pull into. We can pull in the config map object that we're creating out there. And this is great. It's used by deployment, but the challenge with this still is if the config map is changed, the deployment has no knowledge of it out there. So if we go out and edit the config map out there, there's nothing to tell the deployment that it needs to pick up a new value. It needs to pick up a new config map out there. So if we generate a config map out there, like this one we have, then if I go ahead and if I were to apply it, so if in other words, if I edited the config map I had, then I were to go off and just apply that into the cluster, then I would see something output that says, hey, your config map is configured, but note that the deployment stuff out there says unchanged. So even though we've changed this value that our deployment should be depending upon, nothing has triggered the deployment to actually pick that up, that change out there. Similar sort of process if we were using secrets out there. So option 2 that we have with Kustomize is a generator model. That is, here we can define something as a config map generator or a secret generator in customization YAML. So we can define that using those terms there, config map generator, you see down below that. And what this does for us, when the customized build is run, it adds a hash onto the generated item reference. So that you see up the top there, when we have our config map, we have a name in there, but we also have that hash added on. And then in the deployment itself, when we're referencing the config map, it adds that same hash out there. So then this means if the config map generator data is changed in the customization YAML and the customized build is done again, the referencing pieces, in this case the deployment, are changed too out there. So if I were to go in and let's say change this database to be prod from where whatever it was before, then I get a new hash added onto the config map in my config map item there, but I also then notices that for the deployment, we have to change that one as well. So if the config map generator data is changed and customized build is done again, the referencing pieces are changed too. They're tied together by that hash. So kubectl applies results in config map. Any dependent items get the new hash for the updated config map out there. So in this case, if I did the apply, you would see both the config map and the deployment that references it also configured. All right, next let's talk about Istio. So Istio, before we start talking about that completely, helps to have the idea of this init containers. We'll talk about sidecar containers with Istio, but Istio, in addition for our init containers here, they're not limited to Istio. The init containers can be used anywhere within Kubernetes there. But the idea is, in addition to having multiple containers, pods can have 0 to many init containers, which run as startup before the other containers, run serially, and they all have to exit cleanly in order for the regular containers to begin execution out there. So we can have over on the right-hand side, you can see the init containers out there. We have just a simple little busy box of volume things in there, and a simple command that it runs to echo out some information there. So Istio is a service mesh. Let's talk about what a service mesh is. Lets you connect, secure, and control services. We're talking about microservices here. We're not talking about the Kubernetes type of server. We're talking about microservices here. But an example of a service mesh would be a network of microservices, the interaction between them. So in this case, a typical service mesh does things like discovery, load balancing, failure recovery, all the things you see on the slide here, metrics monitoring, A/B testing, canary rollouts, so on and so forth, without really requiring any changes to the microservice code. So that's a lot of what Istio buys you here, is that you can use Istio to get a lot of this sort of functionality for free in terms of you just have Istio installed running alongside your other containers out there in the pod. So Istio allows these kinds of functions out there, and it does it by actually installing a sidecar proxy, kind of like we talked about a init container a moment ago. It's a sidecar container, another container running alongside of the other containers with a proxy built into it so that traffic intercepts all the network traffic there and then can do all these different things based on the being able to control or being able to filter or intercept the network traffic that's intended for the microservice out there. How does Istio work? Istio deploys an Istio proxy called an Istio sidecar next to each service. We're again talking about the microservices here. So then all the traffic meant for that microservice is directed to the proxy. So Istio puts itself out there, installs a sidecar proxy, allows it then to intercept the traffic. The proxies then can be governed by policies that are managed through Istio, kind of as a global sort of policy management out there. Each proxy then uses the policies to decide how, when, or if that traffic should be deployed to the microservice. So Istio sits out there kind of like a traffic cop having the sidecar out there inside the pod, and then based on how it intercepts the traffic and can decide what to do with it based on policies that are set in there. This also enables sophisticated techniques such as canary deployments, fault injections, circuit breakers. These are various patterns out there. Canary deployment being things like traffic shifting when you're trying to roll out a new application, a new version of your application out there, being able to shift part of the traffic over to it for a while, then shift a little bit more over to it, and so on. And as long as it doesn't fall over, then you're good to go. You can move all the traffic over to it. Fault injections, being able to, if you're testing an application especially, periodically inject faults in there. Things like a 500 error that you might get back from HTTP process, or delay in a certain number of milliseconds in there, those kinds of things in there. So Istio runs a Linux container in the Istio Kubernetes pods using Istio's sidecar, meaning just another container that is inserted into the pods to run alongside the other pods out there. And when required, it injects and extracts the functionality based on the configuration needed. So you can set up Istio to automatically inject these sidecars into the pods out there so that it can then serve as that proxy for it. The data plane in Istio architecture, we talk about some terminology here. Data plane is composed of a set of intelligent proxies, these Envoy things, that are put as sidecar containers in there. The proxies mediate and control all the network communication out there, along with using this thing called Mixer. This is one of the primary components of Istio, which works with the different sidecars out there. So the idea of the service mesh is this mesh is made up of a series of these proxies, these sidecar containers that are put into each of the pods out there, but they're all controlled back through Istio, back through things like Mixer out there. And Istio has this data plane. This is what the data plane is, the sidecar proxies and Mixer out there. Then the control plane, which is the other part of Istio, of an Istio setup, manages, configures the proxy to route traffic. It also configures mixers to enforce policies, collect telemetry. So again, this idea that Istio is kind of managing all of these proxies for us and controlling all the things out there that they need to do. Taking a look here at a visual kind of representation of Istio, talking about the service mesh and the data planes. If I have a cluster out here, say I have a cluster and I'm running multiple microservices out here, 3 microservices, then how is the service mesh implemented? Again, the microservices exist in the pods. Traffic is ultimately routed to them. So without Istio in the picture, without Istio, the cluster traffic gets generated and to the pods and between the pods. There's nothing in there to filter it, nothing to intercept it. When we talk about using Istio, we're talking about injecting this additional container into each one of these pods to the Envoy sidecar. Envoy here is the name of the proxy. It is written, the original version of Envoy was written by Lyft, the rideshare company out there too. We have a modified version of it running in here, but we put these proxies in beside each one of these in these pods here. Then all the network traffic goes through the sidecar proxy first. Istio routes all the network traffic, make sure it goes through the proxy here, and then we get the communication, instead of going through the microservice directly, it goes through these Envoy sidecar proxy pods first. Microservice instance is only aware of its local proxy, not a larger network. So we put this installation, this traffic cop in there in front of the microservice. So the microservice only gets what's sent to it or what's let through by the Envoy sidecar proxy out there. Distributed network then is abstracted away for the microservice programmer. They don't have to worry about as much of that. So Envoy again is a high performance proxy. It's just developed to manage all inbound services coming in there. And most basic Istio functionality comes from Envoy itself, load balancing, fault injection, etc. out there. The nice thing about Istio here is I can do with these proxies in there, I can have them do things like the encryption or traffic shifting and all that. And I don't have to change any code in my microservices. That's the idea. The proxies intercept the traffic, do what they need to with it, and I don't have to change any of the code in my microservices. I don't have to deal with all these different things within my microservices if I rely on Istio and have it installed out there. The data plane with Istio. Sidecar proxies make up the data out there with Mixer. Mixer is the Istio component that's responsible for policy enforcement in there. So basically, it's managing the policy for the different sidecars out there. And so we have the adapter out there we can use, and data plane then provides service discovery out there, authorization, authentication, routing, load balancing, and observability out there. So overall, the data plane looks at, translates, and forwards each network packet that goes in or out or goes in to or comes from the corresponding microservices that the proxies are in front of. That's the data plane, the set of proxies and mixer there. So besides the data plane, the other main part of Istio is considered the control plane. What is a control plane? The control plane takes a group of individualist, stateless sidecar proxies, creates a distributed system from them, meaning that it helps to manage the sets of sidecar containers that we put into the pods as a unit out there. Some of the features of this are automatic load balancing, fine-grained traffic control, pluggable policy layer configuration API. In other words, being able to configure this and control how they handle the network traffic that comes into them. Remember again that the sidecar container out there sits in front of the microservice and handles the traffic for it. Also, the control plane is responsible for gathering metrics, logs, traces out there, and ensuring that the service-to-service communication, the microservice-to-microservice communication, is secure. The different components of the control plane are pilot, which configures all the Envoy proxies in the mesh. Again, think of these sets of sidecar proxies working together as being the mesh out there. Provides service discovery for the sidecars, and it's the core component for traffic management. So it helps configure all the proxies to work the way we want. Galley, which is distributed distribution and centralized configuration management out there, installates rest of Istio components from Kubernetes, and validates config from the users. Then there's Citadel, which is the security piece of it, providing strong end-user authentication between services using mutual TLS. Has built-in credential and identity management out there as well. So let's talk about a few of the Istio Kubernetes objects here. The first one we'll talk about is a gateway. So a gateway describes a load balancer at the edge of the service mesh, taking information in from outside. So receiving incoming or outgoing HTTP or TCP connections. There's a spec for it, which looks just like any other Kubernetes object, as you'll see on the right. There's the API version. There's the kind gateway, and there's metadata, my gateway out there, a name and namespace, the same sorts of things, and then a selector as well to select with it, and then you see the other information in there too. So think of this as just yet another kind of object that Kubernetes understands when you're running Istio out there. The spec itself describes a set of ports that should be exposed, the type of protocol to use, configuration for the load balancer, etc. out there, and sets up a proxy access load balancer exposing port 80 for HTTP traffic and 443 for HTTPS, and so on. It can be applied to the proxy running on a pod with a label such as the app My Gateway Controller out there. You see the selector out there. Another kind of Istio Kubernetes object is the virtual service. The virtual service defines a set of traffic routing rules. When a host is addressed out there, each routing rule defines the kind of matching criteria for traffic of a particular protocol. The virtual service is what allows us to kind of split up and steer the incoming traffic out there to different services, different within Kubernetes. So the traffic source can also be matched in the routing rules to allow it to be customized for client context out there, meaning the prefixes, the URLs, those kinds of things. If you look on the right there, you'll see the HTTP section. You'll see what matches it out there, the URIs, different prefixes, those sorts of things out there, and then you can see how it gets routed based on what it matches there. So, for example, all HTTP by traffic default goes to pods of the review service with label version v1. HTTP requests a path starting with WP catalog, consumer catalog here, get rewritten to the new catalog and sent to pods with label version v2. So we can redirect traffic, we can split out traffic, we can filter traffic as we need it using the virtual service. The virtual service relies on having the destination rules out there, which work with the virtual service and declare the subset or version of route destination out there. So it helps us to identify that a certain particular service out there has subsets. In other words, the version, if we select a service version by a label, for example, the V1 version of the service, then gets traffic routed to it for it with on the V1 name there. The one that's V2 has that label on it, that selector gets stuff routed to it for V2. This ties back in with the virtual service before. Now note that when we talk about services here in terms of the host, you'll see on the right hand side this sort of syntax reviews.prod.service.cluster.local out there. We are talking about a Kubernetes service out there. So the Kubernetes service actually then is in, when we talk about virtual services, destination rules, is the service we're talking about versus microservices. I know it's a bit confusing, but when you see things written out here in this sort of syntax, in the host syntax here, reviews.prod.service.cluster.local, is talking about a service running on the local cluster out there. So this is talking about a Kubernetes service, which is the host when we're talking about routing traffic here and sending things here. Some virtual service variations allow us to do some of the advanced functionality we can get with Istio out there. One is the fault injection abort setting here. It's a specification to allow us to prematurely abort a request. So why would we want to do that? Well, think about it from the testing standpoint. If you wanted to, say, every so often throw a 400 or 500 or something error out there, HTTP error, back from your application or while you're testing it or trying it out, this would be one way to do it. You can see here again, it's a virtual service type of object. You can see the same kind of Kubernetes definition as before. You see the host there. Again, think of that as the local Kubernetes service, that cluster.local on the end of it there. And then you see we have a route out there for, and periodically, every 1 out of every 1,000 requests, we're going to send back an HTTP status code of 400 out there. Another variation is the injection fault delay out there. This is similar to the idea of sending back a return code or how often or how we do that. But in this case, we're going to send back a fault out there every 1 out of every 1,000 requests to the V1 service. And again, it's all within that spec that you have out there for the route, as you see down there at the bottom of the slide. So the big picture of Istio here, let's try to tie this all together. We have the control plane, the data plane out there, but at the core, Istio is extending the functionality of Kubernetes. It still requires a deployment and a service out there that we have up and running. We have a deployment out there for my current app, for example, and we have metadata associated with that. We have services in front of there. So it doesn't take the place of these Kubernetes objects, but it augments things out there to extend the functionality. In addition to control plane and data plane portions of Istio, as we talked about, then we have the additional pieces for routing functionality. We have the gateway, which has the load balancer out at the edge of the mesh, configures how proxy load balance HTTP and other kinds of traffic in there. Doesn't do any traffic routing, but does have virtual services then that configure to have the list of routing rules. How do we want to split up? How do we want to redirect traffic in there? Based to different versions of services, for example. Controls how proxies route requests for a service within the mesh. Then we have the destination rules that actually define those subsets or those configurations that we want Istio to apply to request after we get the routing rules on the virtual service. So the gateway allows us to get information or traffic in. The virtual service then allows us to split it up or filter it based on some sort of criteria in there. And then destination rules help us define the subsets, the different sets of services that will handle which kind of traffic, which tie back into the virtual service. So if we're looking at this, the gateway is bound to the virtual service to specify routing in there. So think of those yellow and blue ones as kind of being like a little yellow and blue funnel looking things as being like filters out there, funneling the traffic in different ways. So the Istio components do run in a separate namespace within Kubernetes, one called Istio System when you install it. So that is where the app namespace, the pieces of Istio exist there in the application namespace or whatever namespace you have for your product out there. And then there's the Istio System namespace where the different pieces of Istio, the main core parts of it, live and run there. So let's take a look at some kind of example visuals on to help us think about some of these items. For example, routing examples. We have traffic represented by the green arrow coming into the gateway there, going through our filters out there. And if we're doing the sort of traffic shaping or traffic shifting functionality there, we might, for example, take a large portion of our traffic and redirect it to the current version of our app. You see on the top of the slide on the right, the high level, the app current deployment out there, which would have the current version of our service. Notice that it has a version called current out there as a label in it. And then we would take the smaller portion of our traffic and redirect it to our newer version out there. So we have a smaller portion then that can go and talk to the newer version to make sure that it's going to support the traffic and going to work as expected out there. When we actually then have confidence that it can support that level of traffic, we might increase a little bit, take a little bit more off of the current version, put a little bit more onto the new version out there. This is the kind of canary testing out there we can think about. So then we have a larger portion we route over to the newer version of our app, lesser to a current version of our app, until eventually we can get to the point where we feel confident that the newer version of our microservice out there, our application, can handle all of the traffic load and we can shift it over entirely to the new version and deprecate the current version of our app out there. One of the other examples here, fault injection. Let's suppose that with fault injection, we set it up so that we send traffic to our current microservice. Perhaps we're testing it out here. I want to see how it responds. But every so often, as indicated by the red arrow, we do send a fault over to it. We have Istio generate a fault, so we can make sure to respond to that correctly. So again, the idea of we send out these traffic. Most of the time it's fine, but occasionally we inject a fault in there just to see how it works and see how it handles it in there. Likewise, delay injection, same idea. We will have a set of traffic generated in there that typically goes at a regular pace out there. However, every once in a while, we'll inject a very slow set of traffic there to simulate things like network latency out there. A slow web, a slow network out there. Make sure our application handles that well. All right, now we'll move into talking about the operators, Kubernetes operators, and we'll talk a little bit about some things that we need to understand up front to have a little bit of prerequisite knowledge for that. In particular, we'll talk about scaling resources in Kubernetes, replica sets versus deployments out there, and role-based access controls, the kind of permissions we need around Kubernetes and how we manage that. So scaling here, let's talk about scaling first. So scaling allows you to scale resources up down via the command lines. So for example, I can say kubectl scale replicas equals 3 out there, and it's to scale replica set named foo. Note the RS abbreviation in front of foo out there. Or I can say scale a resource specified in a particular YAML file to a certain number of replicas out there. Or I can say if the deployment names, in the third example, if the deployment name MySQL's current size is 2, scale it to 3 up there. So then it goes ahead and checks to see if the current value is a certain one. If so, scales it up there. Scale multiple replication controllers. We can scale objects within Kubernetes pretty easily. This is a manual scaling out there where we actually run the scale command from the command line out there. Now, what do you think happens if you scale a resource to 0? Well, if you scale a resource to 0, that's effectively leaving it running but turned off, or leaving it out there but leaving it turned or having it turned off out there. Scaling a resource to 0 can be an effective way to leave it in the cluster out there, so it's easy just to turn back on as opposed to totally getting rid of it and deleting it out there. So scaling to 0 can be an effective way of scaling a resource down to turn it off effectively, not have it use any resources at the moment out there, but still have it present in the cluster, and then you can scale it back up when you're ready to turn it back on. Kubernetes scales the number of replicas within a given range to maintain a preset level of resource out there if you use the autoscale function. This is the kubectl autoscale. The other slide was using the manual scaling command out there. But for example, in this one, we have kubectl autoscale deployment out there. CPU percent equal 50, min 1, max 10, says defines an HPA that maintains between 1 and 10 replicas of pods. An HPA in this case is a horizontal pod autoscaler, meaning that it could automatically scale up the number of pods there it's based on wanting your replicas to maintain an average of 50% CPU usage in this case. So if we want to have them maintain a certain level of resource usage, CPU usage here, then we can tell Kubernetes to automatically make that the case. So we have the number of pods that will give us that desired CPU usage between the minimum and maximum that we have out there. So we can have it auto scale for us again. Again, think of that thing we discussed earlier with the idea of Kubernetes acting like a data center to scale the load up based on need or to scale it down based on saving resources out there. So this is one way to do it out there, to have it auto scale for us. You can certainly scale it manually as well, but this lets Kubernetes just take care of it for us. Again, that idea of Kubernetes kind of managing the containers, running the pods like a data center would manage the systems out there. Replication controller, it's worth talking about replication controllers here versus what we call replica sets and stuff these days. Replication controllers, copies of a pod, manages a set of pods, ensuring it clusters in the desired state. So this is the idea behind the way we would formally manage replicas in there. Has all of these kinds of things. And so when we talk about that, replication controllers are criticized for being too imperative, meaning, again, imperative, the idea that we tell them how to do things as opposed to declaring what we ultimately want and having the system figured out. And they weren't considered flexible out there. So they've been replaced then by replica sets and deployments, as we've been talking about those items throughout the course here. So the kind out there, if you see on the right-hand side there, again, just a representation of a deployment. Remember again that deployments have replica sets in them, or replicas in this case, I would call them. And then we have the specs in there for our actual containers that go into the pod, the actual pod spec out there. So replica controllers, if you hear about those, are replaced by replica sets and deployments. Replica sets are responsible for managing pods, scaling instances out there. Deployments have additional functionality out there like rolling updates and such, but deployments encapsulate replica sets and pods out there. So deployments are the basic name. Replica sets contain the deployment name plus the unique identifier. Pods contain the replica set's name plus the unique identifier. The point of this is simply pointing out the sort of relationship here, the hierarchy between them. At the higher level, we have a deployment with a specific name that we give it out there. Then the replica set, being a part of the deployment out there, gets its name based off of the deployment plus a unique identifier out there. And then when you have pods, pods contain the replica set name plus the unique identifier, some hash out there. The reason for this is because we can't have, the reason for the hash part, is because we can't have things with the same name in a namespace there within Kubernetes. So we can't just use that like a pod name out there for multiple instances or multiple pods. So each pod has to have this unique hash or identifier on it to designate it, have a separate name rather from the previous pod. So next let's talk about role-based access controls. How do we secure Kubernetes? So why do we need role-based access controls in the first place? Because in a real-world Kubernetes environment, we may need to have things like multiple users with different properties, establishing a proper authentication mechanism out there, have full control over which operations each user or group of users can execute, have full control over which operations each process inside a pod can execute. So realize here that RBAC is not just about human users, it's also about the processes inside of Kubernetes and the permissions they can have. And we may need to limit the visibility of certain resources of namespaces out there. There's three elements involved when we talk about RBAC out there. The set of users, the subjects, which are the set of users and processes that want to access the Kubernetes API. Again, the idea of there's both the human users out there as well as the processes. Then there's resources, the set of Kubernetes API objects that are available in the cluster. These are all the things we've been talking about throughout the course. Pods, deployment, services, nodes, persistent volumes, those kinds of things out there. And then verbs, the set of operations can be executed on the resources above. So if we think about what a human user might do to a particular object in Kubernetes, the kinds of things we'd run from the kubectl command line, we're talking about things like get, watch, create, delete, etc. Ultimately, all of them are this CRUD, create, read, update, or delete kinds of operations out there. We think about the set of things that we're trying to connect together here. We have subjects, which again are the people or the persons or the processes out there. Could be an operating system process, a process in a pod out there. The API resource is the kind of objects we talked about within Kubernetes itself out there. And then the operations that are available out there as verbs or things to list. So we want to connect the subjects, the API resource, and the operation. In other words, we want to specify, given a user, which operations can be executed over a set of resources out there. So one of the ways we do that is a Kubernetes object called a role. So the role connects API resources and verbs. For example, if I want to be able to list pods or to create a namespace, that sort of things out there, connecting up the actions with the objects in Kubernetes there. Can be used for different subjects, and this is bound to a namespace. So we also have Kate's cluster role. So in RBAC, when you see something without the word cluster in it, it means it's a namespace scope. It's intended for use in a particular namespace. When we see the cluster as part of the name, that means it can be used across the cluster there. So the role binding then, so a cluster role in this case would be that across a cluster, we would connect up one of the API resources, one of the object types in Kubernetes with the different kinds of verbs or with the verb we could use on it there. The role binding then takes the role and binds it to a subject, meaning it binds it to a user or a process out there. Given a role that combines the API objects and the verbs, defines which subjects can use it. The cluster role binding, as you might expect, then takes it, connects subjects to cluster roles out there. Again, that sort of cluster scope as opposed to namespace scope in Kubernetes. Here's some simple examples here. We have a role binding. We have a role here that allows us to do the list, get, and create those verbs against the pod resource out there. And then we want to actually have a particular user who can do a role binding with that to actually connect up to the role that we have out there. You can see again, these are simply Kubernetes objects out there. Kubernetes objects that are connecting things together. The role defines the actions that we can do against the objects in there. And then the role binding binds that to some subject out there. So that means that in this case, this user could do these kinds of things. They could get pods, that's allowed from the role who says to be able to get pods out there. You can describe the pod, create a namespace out there, those kinds of things that are described, but they wouldn't be able to do things like get the pods from a different namespace or get the pods with the -w, which would require the watch action or the watch verb to be included in the permissions. In Kubernetes RBAC, users are global, user things are meant for global or meant for humans or processes living outside the cluster. The service accounts are for our namespace, meant for intercluster communications or processes running inside the pods. Both will authenticate against the API to get access to resources, but there is no true Kubernetes user object out there. So you can't do a kubectl create service. You can do a kubectl create service account name, but not a kubectl create user. The bottom line is the cluster doesn't store any information about users, so that has to be managed outside the cluster where certificates or tokens or some of the usual mechanisms. So RBAC providing access, if we want to take a look at an example, providing access to an application and deployment. Here we can see sort of a Helm template in this case that has the service account for RabbitMQ out there. If we have the RBAC enabled there and the Helm, this is another kind of feature of Helm, for example. I could go through and say if something is enabled out there Then we can define a role allowing get verb to an endpoint, and then the role binding connects the service account and the role out there together. So that then we have that service account for RabbitMQ able to do the get on the endpoints out there. All right, let's move into talking about actual Kubernetes operators here. So Kubernetes operators, what is it? Well, it's an operator is a method of packaging, deploying, and managing a Kubernetes application. It's basically a way to extend the functionality of Kubernetes and to customize it and to provide a way for things that are not typically runnable or usable in Kubernetes to be able to use them in there. What I mean by that is simply that if I have something that is a stateful application, meaning that it needs to it normally tries to maintain a state with the object. It's not stateless, such that it couldn't, if it normally was killed off by Kubernetes, you couldn't just start up a new one, but you had special handling you needed to have for a type of object you wanted to run in Kubernetes. Operators allow you to do that. So Kubernetes application, in this case, is an application both deployed on Kubernetes and managed using the Kubernetes API and kubectl tooling. Kubernetes, by definition, by default, is going to want to be able to manage your application as a stateless sort of application, or that means that it can kill it off and restart it if it needs to. It can easily scale it out there. Your application is ready to respond to these kinds of requests for Kubernetes and behave as Kubernetes would expect it to or needs it to out there. If that's not the case, then an operator can actually be used to have, as we said in the slide here, purpose-built running a Kubernetes application operational knowledge baked in. Being smart enough to understand and to handle from Kubernetes, if I need to run things differently or if I need to do things in a way to respond to Kubernetes, I can have an operator that will take those Kubernetes actions that Kubernetes tries to do and interpret them for my object, and then have my object still be running out there, but still behave or respond to Kubernetes in the way that Kubernetes would expect right there. Cloud-like capabilities and code-to-operator code can provide an advanced user experience, automate features like updates, backups, and scaling. You can have additional functionality built into your object. If you have a particular type of object that has a certain way it needs to be backed up, that doesn't really correspond to the way Kubernetes would be doing things, or updates, or those sorts of things, or scaling, you can build that logic into the operators there. So all of this is accomplished using standard Kubernetes tools, the CLI and the API. So one of the pieces that's out there to be available to use now, designed by CoreOS, but now part of Red Hat, is what's called the operator framework out there. The operator framework has several pieces. The main one is the operator SDK, which is designed to make it easy to code up operators without having to know Kubernetes API details. And then it has a lifecycle manager to oversee the installation updates, management, lifecycle of operators out there, and also operator metering in there, which is intended to be able to support usage, or enable to support usage reporting for operators that provide specialized services. Operators can be coded up in Go or Helm or Ansible. Go is the main language out there that you'll want to really probably use if you're going to have an operator that's intended to do anything more than just do sort of an initial deployment of items in the cluster. It's trickier to do any kind of thing like Helm and Ansible, to do sophisticated operators with those, simply because those are more kind of one-time deploy things out there versus the Go code, which allows you to code up more sophisticated operators that respond in the way that Kubernetes would expect out there over the life cycle of objects in the cluster. How do operators work? Kubernetes is essentially a desired state manager, as we've talked about. We provide the desired state via a spec, and it makes it happen and tries to keep it that way even if something goes wrong. We talked about this controller idea, the control plane on the master there. It includes controllers out there that try to reconcile the state by monitoring the state of existing objects, out there, comparing their object state to Kubernetes YAML specs, the specifications we give it in the YAML files for what we need in terms of services, deployments, pods, those kinds of things. And if there's a difference, to try to correct it. In other words, we have things running out there, we have something go down, it doesn't match the spec anymore, the number of things we've declared we want. So Kubernetes tries then to reconcile that by creating enough to make sure we have the number we want based on the spec that we have out there. Native Kubernetes objects, deployment service, etc., all respond well to this model because, again, they're considered stateless. This is the idea of they can be deleted, destroyed, and then recreated and automatically pick up where they left off. But the model has issues with more complex stateful applications, such as a database running on multiple nodes out there. If the nodes go down, we need to reload the data to get back to a previous good state. So the typical cloud-friendly like operations like scaling, upgrading, disaster recovery for these kinds of stateful apps don't fit out of the box. So to handle this, we write operators to extend Kubernetes to allow defining a custom controller to watch your app and do custom processing. The applications to be watched by the operators defined as a new object type in Kubernetes, a custom resource. So we hear the terms custom resource and custom resource definition, which are essentially your custom objects in Kubernetes. They're not a deployment, not a service, not one of the standard types of objects. They're custom objects out there that you want to run in Kubernetes, and you have a custom resource definition that defines the spec for those, and then the custom resource that runs in Kubernetes, and the operator that runs around the custom resource to make sure that it responds in the way that Kubernetes expects out there, typical kinds of operations. So the overall behavior of an operator's controller, a controller that you write as part of an operator, is similar to how the native Kubernetes handles reconciling those objects out there. Operators give you the chance to do custom processing when you're reconciling things there. On this slide, you'll see an example of a custom resource definition out there. Again, it'll look familiar at the top, kind of API version again, a kind, metadata, and a spec that's associated with it there. So the Kubernetes API server creates a new RESTful resource path for each version you supply, the REST interface out there. The CRD can be scoped either for the namespace or the cluster, similar to how we talked about like the RBAC stuff out there. And it has a scope field in it out there as well. And then you'll see things in there as well in terms of like the names we can use, the plural, the singular, the kinds of things out there. We can manipulate just as other objects. We have this to spec and we apply it. And here's the RESTful API endpoint you can see for this one, the cron tab in there. You can look at, see an example of that. The endpoint URL can then be used to create and manage custom objects. And the kinds of these objects will be the kind that you defined in your specification out there. For example, cron tab in this case. You can then make instance these custom objects and use them with operations like kubectl get. So once you define an object that is out there, a custom resource, you can use it just like any other Kubernetes object with the standard, list or the get out there, creates, deletes, those kinds of things out there. So Operator Hub IO, this is the operator registry for Kubernetes operators out there. This is supported by Red Hat, and it is a way to surface your operator out there to the wider community to let people know about it, know what it can do. And so if we want to have an operator that manages things for us, we can just have that available out there and have people be more aware of it and be able to use it. Let's next talk about GitOps. What is GitOps? GitOps is a way to do continuous delivery. It works by using Git as a source of the truth for declarative infrastructure and workloads. Per Kubernetes, this means using a Git push instead of kubectl create apply or Helm install upgrade. What are we saying here? We're talking about being able, instead of having to do things via the kubectl command line out there, between just relying on users to do things via the command line and getting that right and things. Instead, we manage our YAML specifications in Git. That is, we put the files up to Git, and then there is something, maybe it's an operator or a specialized process, that identifies that there's been a change in the Git project, much like sort of a CI thing, if you know what continuous integration is, but identifies there's been a change in the source repository for our YAML files, our specifications for Kubernetes out there. and actually identifies the change and then goes off and applies those to the cluster for us. So instead of having to interact with the cluster through through the Kubernetes command line out there, we simply make the change within the spec and then put it in Git, and then Git applies it to the cluster. So why would we do this out there? Well, for a couple of reasons. One is if we can manage things as code, meaning we manage things in a Git repository here, then we have that way to actually do things with the file in code out there, as we would for any other source code. We can do code reviews on it. We can track changes over time. We can do diffs on it. We can even roll back easier because we could just go back to a previous version of the files stored in Git and be able to use those. So if you think about it from the standpoint of a user actually running a kubectl command line out there and making a change to the cluster that way, if that user messes something up, or if we need to know what they did, they've gone on vacation, whatever the case may be, then we don't have that information. We only have some record in there of something, but we don't have as easy of a way either to roll things back or to see what the differences were or do that. However, if we manage our manifest for the cluster through Git, we're able to actually take advantage of all the things that Git can do in terms of differences, looking at the code, so on about that, and be able to do that with our Kubernetes manifest instead of having to manage it by person. So in traditional CI/CD pipelines, CD per CI process creates build artifacts to promote them to productions out there, continuous delivery versus or per the continuous integration. In a GitOps pipeline model, any change to the production must be committed in source control prior to being applied to the cluster. Should ideally be done through a pull request or a merge request, those mechanisms in the source management system where we can merge things in out there, create them. The advantages of this is code review for changes, tracking of who did what. Again, rollback is via Git. You can simply go get back and get a previous version of things out of there. The whole infrastructure can also be recreated from source control. That's another key point here, is that if I have all of my specifications for my cluster in Git, then if something bad happens to my cluster, I can actually just run this process again. All the specifications will be in there, and it will go out and create those for me, recreate the cluster based on the specifications stored in Git. GitOps is Kubernetes, so what do we need here? We need a Git repository with our workload definitions in YAML format, Helm chart, any other Kubernetes custom resource that defines our cluster's desired state. This is the config repository out there, the set of Kubernetes objects out there, a set of YAML files out there. A container registry where our continuous integration system pushes immutable images. What do we mean by that? Basically, think about this a couple ways. Even though we are always telling Kubernetes what to do and what to have via the manifest, at the lower levels, what Kubernetes needs to do is still spin up containers that run within those pods. And the way it spins up containers is from the images that we've talked about all along, the Docker images out there or whatever process used to create the images. And so we still need to have a place to get images. So if I am updating some resource in there, for a pod spec, for example, to a newer version of a microservice, I need to have a newer version of an image that's based on. So I need to be cognizant of having both a repository for my specifications out there, but also one for the images that I need to use in there. So what we would need also, in addition to those two repositories, one for images, one for our YAML files out there, is an operator that runs in a cluster and does a two-way synchronization. So it would watch the registry out there, the image registry for new image releases, based on deployment policies, update the workload definitions in there, and committing the changes to the config repository based on those. Then we would go out and update the cluster, or we go out and update the cluster for us. So watches for changes in config repository and applies them to our cluster. This is just a quick example, a diagram here, looking at the idea of having the users out there pushing Docker containers out there, or images rather, into a repository or registry, committing things into a Git repository for YAML specifications. There are different products out there, like the Weave Flux one, for example, which we then go out there and can apply via Helm or some other orchestration thing the stuff into our actual deployment out there, into our actual cluster. Let's talk about monitoring here. So there are some basic tools for monitoring that come in handy when you're working with Kubernetes. One is the Kubernetes dashboard, which has a visual interface to cluster. It's a general purpose web-based UI for clusters. You can get overall status about objects out there in the cluster. You can evoke it from the command line via, if you're running like a Minikube, for example, a Minikube dashboard or a kubectl apply from location and a kubectl proxy out there. You can also create or modify objects via create link out there, so you can do operations in it as well as getting information about it. But it's basically a way to interact with Kubernetes through a graphical interface there. You can upload a specification file to it, but you can't, and you can type in JSON or YAML as well. So you can create objects out there. You can do specifications in it as well. It's probably most useful for being able to look at clusters and get information from that. There's also a tool called Prometheus, used for event monitoring and alerting. It's an open source application for those types of functions. What it does is it records real-time metrics in a time series database. Think of it as recording information about your cluster over time in a database out there, adding a query language on top of it, and then it has a monitoring platform, which typically has different kinds of exporters that will run on the host to export metrics. Things that will run within your cluster to send out information that can be stored in this over time in this database there. Prometheus then to centralize and store the metrics out there. Alert Manager to trigger alerts. You can have alerts triggered if you're running, short of resources or having issues in there. And then you can also use a tool called Grafana to produce dashboards out there. Grafana is a metrics and analytics and visualization suite, basically meaning that it's a way to build cool graphs. You can have information, for example, that you pull from things like Prometheus. You see others down there. Elasticsearch, InfluxDB, MySQL, Postgres, CloudWatch, all that. Different kinds of data coming in. And it allows you via a visual interface to have different panels, different kinds of graphs to add data in there and get different kinds of information, like what your system is doing over time, those kinds of things out there. That concludes this presentation. Thank you, and I hope it's been useful to you. If you have any questions, feel free to reach out to me at the email address on the screen. Thanks, and have a great day.